All right. Okay. Hello, everybody. It's my pleasure to introduce Mr. Ronald Jarnagan, our first speaker, and his presentation title: Application of Simulations for the Development and Evaluation of ASHRAE Standard 90.1. Ron is currently the principal owner of RLK Technical Consultants, LLC, a company focused on energy use in the built environment. Previously, Ron served as a staff scientist at the Pacific Northwest National Laboratory, where he led a team of researchers focused on energy efficiency in buildings for 25 years. Prior to that, Ron served as a faculty member in mechanical engineering at the University of Florida for 10 years. Ron was the ASHRAE Global Society President in 2011 till 2012, and previously served as the Chair of Technology Council as a Vice President, Standards Project Committee 90.1, Sustainability Roadmap Committee, Sustainability Oversight Committee, Vision 2020 Committee, and Building Energy Labeling Committee. He also served on the Headquarters Renovation Committee that delivered a LEED Platinum renovation project for the ASHRAE headquarters in Atlanta, Georgia. Ron received an Exceptional Service Award from ASHRAE, an Engineer of the Year Award from the National Society of Professional Engineers, a Special Recognition Award from the Association of Energy Engineers, and a Presidential Award for the Illuminating Society of Engineers. In addition, he has been inducted into the University of Florida Hall of Fame. He is also a decorated U.S. Navy veteran of Vietnam, having served in the River Patrol Services there. All right. Thank you.
Okay. Vietnam, if you move, you live longer, right? So, and in research, it works the same way. Okay. So I just want to give acknowledgement to the second contributor here, Bing Liu. This is the young Chinese lady that I hired at the National Lab a number of years ago. And when she walked in and gave a presentation, I was completely stunned with her capability to give presentations, her grasp of the information, her knowledge of what it took to convey information to a client. And I went up and I told the department chairman, I said, I'm going to give you the best advice I've ever given you in your entire life. He said, what's that? And I said, hire this woman before she leaves the building. Because I found somebody, and I said to her, you're my ticket out of here. And it turned out I retired 2 years ago, and she was my ticket out of there, and she runs the program now. So I want to give credit to her because she's one of the people that did a lot of the work behind this. So I'm going to talk to you a little bit about the simulation model overview, a couple of thoughts that I have about that. I'm not a person who talks in academic terms, even though I spent time in academia. I like to have a conversation with you, so that's kind of the way I do things. I'm going to tell you a little bit about the background standard 90.1, so for those of you who don't know what it is, you'll kind of be able to put it in context. And then we'll look at what's special about this within the ASHRAE arena. And then I'm going to show you some things that look at what we call a progress indicator that you'll see as we're developing this standard on a continual basis, how we keep track of where the energy savings are, almost in real time while we're doing it. And then look at some of the energy saving results and then have a little bit of time for questions. So next slide. So this is kind of an overview of simulation models. And when we're talking now about simulation, I'm talking about whole building simulation. Annual simulation of the building, all the systems in there, the components in the building. So probably some of you may, how many people in here are actually modelers or simulators or have had any experience in that? A few. The rest of you might just clueless, but this is a 250,000 lines of coding that actually simulates a building on an hour-by-hour basis under the influence of all the climatological variables. And so if you go to the United States Department of Energy website, which anybody can do, there's about 30 plus or so energy simulation programs that are free to the public, as well as a large number that are not. Their focus is really on energy simulations, so it's what we call the 8760. That's how many hours there are in a year. So they just march through the year, and that's what they do. Every hour, they try to bring the system to equilibrium, and then they calculate the energy. We're going to look at Energy Plus, which happens to be a DOE-supported free tool. What that means is that anybody, anywhere in the world can download that if you want to. Now, I can tell you that you've never run an energy simulation before. You're going to get into tall weeds very quickly. not easy. That's why there's not a whole lot of us that do this kind of work, because you kind of got to be about half crazy to do it. It'll drive you nuts most of the time. I'm completely crazy, but Bing was only half crazy, so she got to do the work. The lineage of this was a couple of programs that existed from various government agencies in the United States. The old BLAST in '02, they became a new Energy Plus program. Interesting thing was it turned out that we had one government agency that was writing one program. We had another government agency that was writing the other program, and they both did basically the same thing. And the weaknesses of one matched up with the strengths of the other and vice versa. So I walked into a meeting one day in research and I said, why do we have two of these? And that caused the Energy Plus to be built of those things coming together. I didn't want to write them, I just wanted to use them. I didn't understand why we had to make choices between the two. And robust simulations require a lot of detailed, reliable, long-term climate data, like hourly temperatures, humidity, solar radiation, and you need that in coincident measurements over long periods of time. We actually use 30-year data, okay? 30-year data that's produced. Okay, next slide. So here's some of the pros and cons if you haven't done it. This is what they do well. They save computational time. If you had to do this by hand, if you started now and you're a student, by the time you retire, you probably have the first run out of the way. Okay. So they save a lot of time. They produce repeatable and reliable outputs depending on the inputs. You have to understand what you're giving it. They produce more detailed reports than you can possibly imagine. You never want to print the output of one of these things out. You love these computer screens so you can find them. There's about 10 pages in the output you actually need, but they give you plenty of information. And the results can be compared to other studies easily because we know the tool that's doing the calculation and we know how it works. So it's repeatable in that sense. So where are the challenges? Well, it takes a knowledgeable Yes. Input can be absolutely tedious if you don't have the tools and the interfaces. There's just lots of, you have to tell it everything because it knows absolutely nothing. The parameters need to be processed before the input. If you have an air conditioning unit that has an EER rating, the ones that are rated like that, you can't give it an EER. They don't know what an EER is. You have to break the fan power out, invert the numbers, and hand it to the simulation like that. So it's a fair level of complexity and skill that needs to be used to do this. It actually will accept parameters that don't reflect reality. It really will. It'll just take numbers that are completely out of bounds and it has no sense of whether that's good or bad. So be careful if you have somebody that's not knowledgeable providing the input. And you sometimes struggle with renewables and new technology where it doesn't have algorithms to handle that. Next slide, please. So I'm going to talk a little bit about Standard 90.1. And this is ASHRAE's sort of flagship standard. It's a commercial building, essentially a commercial building energy standard. And it's got a heritage that's been around for a number of years and various evolutions. And in the last probably decade or so, we've been on a cycle in which we've been updating this on a 3-year basis. And we've gotten pretty aggressive about how far we were going with some of this stuff. And I wanted to kind of show you what we've done with this and how far we're pushing it. You know, we talk about the green building standards, but I can tell you that the baseline minimum standard, which is used as the basis for almost every state's energy code in the United States, and it's used in many other countries based on things, I can tell you that that standard today is what you would call the green standard probably 10 years ago. I mean, it is. The baseline standard is getting pretty tight. A number of years ago, I foolishly got talked into being the chair of the committee that did this. And I will say that I don't know whether I'm proud of this or not, but I'll tell you this number. I hold the intergalactic record for the number of comments that was ever registered on an ASHRAE standard. 80,000 public comments. Now that's kind of a dubious record, right? That's one way to look at it. The other way to look at it was there was a whole lot of people in the country that really cared about what we were doing and registered things. Right? So you can look at it the good side and the bad side. 80,000 public comments. Nobody has ever had that many registered. Clearly we did something wrong. No, we did something that made a difference. And a lot of people wanted to say something about it. Okay, next slide. So this is the energy standard for commercial and mid-rise to high-rise residential buildings. once we go into higher rise, which we consider 4 stories and above, the construction, at least in the United States and in most other places, starts to look like regular commercial construction. Below that, they look more like residential, right? There's structural issues that come in, there's elevator shaft vents, there's many things that come into the standing. Next one. I didn't realize I had those things on coming out all the time. This generally forms the model energy code for commercial buildings, and in 1992, the U.S. passed this Energy Policy Act, and a couple of things that they did is they made 90.1 the law of the land. It said every state has to adopt 90.1 or equivalent. Now, in the U.S., we have certain rights that are reserved for the states and some for the federal government, and actually the Department of Energy can't say that, because they have no dominion over that. Codes are states issues, they are not federal issues. But the feds wanted this to happen, so they made this statement. And while they can't punish you for not doing it, they don't give you extra money to implement stuff if you don't do it. So that's how they actually use the incentive on that. But the other thing it did, the last one on the list, is this is one of the reasons why we got a lot of comments, is that in that legislation it said that the baseline efficiencies for mechanical equipment, your chillers, your unitaries, your packaged equipment, all these things like that, the numbers that were established in this standard would be evaluated by the U.S. Department of Energy, and if those were found to save energy, those would become mandatory standards on the manufacturers for making their equipment, so they could not make any equipment less efficient than that. That had never existed before until this legislation passed. Before that legislation passed, the committee size was 17 people, and if you had a meeting at the society where people can come in, because all the meetings in ASHRAE are open, you might have 5 or 6, 10 people in the audience listening, okay? So remember those two numbers. The first meeting after it passed, by that time, we had ballooned the committee size up to 72 people, and I had to hold my meeting in the ballroom because there was 286 people in the audience. Okay, suddenly we were doing something that really made a difference and got in people's space, so to speak. And I'm just trying to tell you that because this stuff that we do analytically and we go out and work on these things like that has real implications, both for energy savings and how it impacts the manufacturing community as well. And one needs to be careful how one does that as we move along. So if you're thinking about doing things like this, just consider these consequences as you do. Next slide, please. It forms the basis for most of our commercial energy codes. I think I may have already said this. And it is also the baseline or the reference standard for your higher performance building designs, your green zones. We have another standard, is 189.1 in ASHRAE, which is sort of the green buildings, and it's kind of linked to LEED a little bit and so on. But those all build off of the basis of 90.1. Okay, so what's so special about it? Well, in 2007, the Department of Energy and ASHRAE signed an MOU, a Memorandum of Understanding. And basically, the U.S. government challenged ASHRAE to write a standard that improved the energy savings 30% for the 2010 standard compared to what we use as our baseline now, which is the 2004 standard. That was a really tough task to do that because we had to make a lot of changes. And in ASHRAE, you can give somebody a challenge to do that, but the committee itself has to make the decision. So you don't have any way, you can't go in there and say, you've got to do this. It's a challenge, and we really want you to get there, but we can't interfere in that process because the committee is the only one that can make the decisions. And so the committee approved a work plan with that same 30% goal. They took the goal and they started there. And so this was the first time that the committee was set up with an energy target goal. In previous ones, they would just work, come up with a new version, whatever they thought was right, and off we go. Now, we got targets, we got performance metrics to hit. A whole different ballgame when you start doing it. Next slide. Next, whatever's up there. So the implication of this was that it was no longer business as usual. Now, somebody came in and said, all right, here's the number, we got to get to the number. And that resulted in an accelerated pace and number of addenda. Next slide or next, whatever comes up. There we go. the 99, I was chair of the committee that wrote the 99 standard. So when the 99 was done up to the next version in 2001, there was 34 addenda. I might stop and say that this standard is maintained on what we call a continuous maintenance basis, in which the committee goes in, makes changes to it in real time, and goes on. They don't just set it on the shelf like they did in 99 for a couple of years and then come back and reconvene a committee and they work on it again. The committee stays in place the whole time, and people flow through the committee as members. So there was 34, then there was 32, and then the 2004 to the 2007 there was 44, and then when you went up to the 2010 standard, there was 109. So there's been 153 done since 2004. Okay, next slide, please.
Mark?
Yes.
Now, the last one, 2010, you have 109. Is that due to other standard employees?
No, they had to get, to get that 30% goal, they had to get a lot more aggressive. They reached, I think I've got some slides on here where we talk a little bit about some of the stuff they had to do, right? We started looking, basically what happened was everybody started running around the building and saying, okay, we haven't done something here. We've already kind of messed with the mechanical equipment, and that's about all the traffic is going to bear on that. We can't go any further on that right now. So where are we going to find it? We started looking more at infiltration, started looking at other things that we really hadn't paid a lot of attention to. And some of them turned out to be very hard to model too, by the way. Because there was a lot of pressure on the modelers as well as the pressure on the committee to make decisions. But I think this was one of ASHRAE's finest hours when we did this. I personally believe that because the committee worked hard. Does that help? Yes. So, when I was at the laboratory, not only was I the chair of the committee in '99, but I had people that were working for me that were modelers that I tasked to do some of this work so that we could do it. Somebody has to run these simulations. It's costly, it's time consuming. And so we provided these. And because the U.S. Department of Energy would take a new standard and evaluate whether it saved energy, and if they did take an action, we needed to know as we were going along whether this thing was saving energy and how much. And particularly when we had the 30% goal, you needed to know where you were. And so I said, why don't we make a progress indicator, come up with a modeling setup that we can use, and then every time we're looking at an addenda, we can evaluate it and figure out what it's going to contribute to the end savings. So the committee always kind of knew where they were. Before, you just did a whole bunch of things. You send it off to the modelers, and 6 months later or 8 months later, or whatever it was, you come back with an answer. That wasn't going to work in this environment with this heavy goal here. The only way it was going to work is to be able to pretty much go back to the lab, run the stuff, give them the answer, let them know where they are. So this really helped the committee to do that. So this met the DOE requirement to do this. The progress toward the goal was kind of a continual thing. It applied in all of the 17 climate zones. I want to talk about the climate zones a little bit when we come up here on one of the slides that follows here. And at every committee meeting, there would be an update from the progress indicator. So we were kind of given something almost in real time, as you understand. And there's some prototype buildings. And that little graphic in the lower right over here, I'll talk a little bit more about those. So this was it. The progress indicator became the one that tracked the metrics every time. So we could always tell the leadership of ASHRAE how well we were doing, and more importantly, the committee who's trying to do this. And that's a lot of pressure we put a lot of people on. They worked really hard at this. They still work very hard at this stuff. I don't think we're going to be accepting any 30% improvement goals in one 3-year cycle anymore. That one was enough. It about wore us all out. But fortunately, I wasn't the chair of the committee anymore on that. By the way, you can get to be the chair of that committee by 2 ways. One, you want to do it and you're really technically sharp and you have the command of that, or the other one is you can just simply be stupid. I took the second path. I was sitting in the meeting. I tell you how I ended up there. I was sitting in a meeting of the mechanical subcommittee back in 1989 or 90 or something like that, and there was an appeal that had been lodged against the 89 standard, and they were trying to figure out a problem with gas water heaters. They had 2 requirements. They had a requirement for thermal efficiency, and they had a requirement for standby loss when the pilots run. And the gas industry didn't like what we'd done. and they sued X-Ray. They sued X-Ray on this thing. And I was just sitting in the meeting. I didn't know anything in the background. I was sitting in the meeting. And they were having this big fight about this. And so I said, hey, you know, what if you just kind of made a little simple model and looked at thermal efficiency and standby loss and said, here's what we really want to have the energy used for this water heater in whole for a year. And we can get it a couple of different ways. More standby loss and less this and more of that. And, you know, you could go either way. And they said, God, how would you do that? And I said, well, you could make up a little model. And they said, would you do that? And that was the fateful yes, right? Now, I learned in the military, don't volunteer for anything. Somewhere I forgot that when I got to X-Ray. So when I say stupid, I mean dumb. I kept making that same mistake every time. That'll get you right to the presidency if you keep doing things like that. So, come talk to me if you have an interest in that. Next slide here. See, a technical presentation doesn't have to be dry and boring. So one of the things that happened in all the versions of the standard that we noticed was that it seemed like every group wanted to have different prototype buildings. If you're going to model a building, what kind of buildings are you going to model? How many of them? And what are you going to do with it? And how are you going to come up with these numbers? So finally, we decided to try to start standardizing these things so that we had standard buildings and that everybody agreed on them and stuff like that. So we convened a simulation working group as part of the committee. We had some representatives from all the subcommittees there. We kind of established what the ground rules were going to be for the modeling. And then we started looking at some of the key modeling inputs and assumptions. And then we wanted to have a way to review the energy savings analysis and results. And the goal was to conduct, when we say a book-to-book comparison, means what's in this standard, written in this standard, so when you implemented all that, what's written in this standard, not what really happens in the thing, but what the comparison of those is. Because what happens in the field is not always what you see in the books sometimes. And we went out to develop some prototypical building types that we could use to model in there. And the ones that are being used today cover about 80% of the commercial building stock. So that's a pretty good representation. You're not letting much get through that you aren't really covering. And then we had to generate the models for all of this whole building energy, which included what we call the regulated and unregulated loads. And I don't know how code enforcement may work in other places, but in the U.S. and lots of countries, they come in and you have code inspectors that come in and look at the building, and they give a certificate to the person so they can occupy the building, right? But a lot of the loads that you have in the building come after you get the certificate of occupancy. There's a whole bunch of plugs around the wall. And as soon as you move out, people start plugging things in there, right? So we can't regulate that because it's not in the building when the inspector comes around to do it. And one of the things that we have found through our research and comparing some of this stuff today is the thing that's starting to eat us alive in energy savings is what's being plugged into these things over here. Now, the good news is, in some ways, computers now are mostly laptops and a lot less desktops. Monitors are LCDs and much lower power, so a lot of things that we're being plugged in are lower energy use, but we're plugging more things in too, right? That's part of the problem. And we don't have a mechanism by which to regulate things. So you try to figure out what else we can lower to make sure we get to some of these points. So that's what we mean by receptacle loads or regulated and unregulated. And of course, this includes everything, the building, as well as the exterior lighting, like on the facade of the building, walkways, entries, and so on. This then allowed the committee to evaluate on a pretty expansive scale what the impact was of every change that they were making before they even made it. We could run the simulation before they actually even voted on things to tell them what they were going to achieve on that. Sometimes you got to figure out how much pain you're willing to take and push back from the public to get a certain number. And by the way, one of the other things that's done in that process is that there's a cost effectiveness that's applied to every one of those things before you make the change. You actually look at this and see whether there's some cost effectiveness to these things. You could obviously just go out and put a lot of things in there, but some things you just wouldn't want to do that for lots of very good reasons. Okay, thanks. So here's kind of how it works. If you just want to look at it in block form like that, we've got these prototype building models. There's 16 of them. You generate this minimally compliant code model for the 2004 and then the subsequent ones. Remember, right now we are using 2004 as the baseline. This is our standard. Everything's compared back to that. We used to always compare it just to the previous one, and that got really confusing because your baseline kept changing. So we decided, let's freeze the baseline. 04 was the one we decided on. We've got 18 climate zones, but there's actually 17 climate locations. And I got another slide to talk to you about the climate things because I think this is important. And then the other thing we had to do is we really wanted to think about what the standards say as a whole. We had to develop some new building construction weighting factors. So we have there's an agency of the U.S. Department of Energy that does these building surveys every I don't know, 6 or 8, 10 years. And it's a statistically valid sample of the building industry in the United States, commercial building industry in the United States. And so we know a lot about where the buildings are, what they're used for, how big they are. And we know some things about the equipment, not much, but we do know some things about it. And so we came up with some buildings that we thought were representative of that. Now the buildings that we might be using might not be buildings you might want to use in Lebanon. If you had some information about the buildings, you could probably come up with something like this. And a lot of the stuff that we use to put this in place is replicable in other places if you have some of the data. So you sit there and you run them in all the different climate zones, you aggregate those up with the weights, and then you have, at the end of the day, you have an aggregate number of this is the impact of this thing. Next one. I keep pressing this button, but it's only going to work if I say next. Speak to me. So the progress indicator, there were multiple ventilation levels. You can see up here we had standard 62 as our ventilation standard, commercial ventilation standard basically. So we got 62.1, 99, 2004, 2007. That one kind of tracks behind 90.1 in a way, because we can only put in the standard a reference to one that already exists. And so if they're producing the standard on the same cycle we are, we can never reference their most recent standard. We've always got to reference the one before that's out there so that we can do the simulations. And then you get these kind of massive simulation runs. Each iteration of the progress indicator requires 1,600 runs or so. You can do the math, see how we got there. We have to go back every time, run all these things, simulate, assimilate all the data, put it together, and out comes an answer. The simulation framework is to do a quick design day run so we get the systems sized right, just like you do if you were doing the job. And then an annual run to calculate the energy use, and then we got automatic process to generate inputs and extracts from there. We do not, if you saw the environment that was there, you would never actually find an independent input file. The input files in our system are made on the fly. We have a template. We give them the inputs, we say this insulation level here, this efficiency level here. Process converts it into what the simulation wants, merges it with a structure that matches the building, lines it up with a climate, makes it run. But we don't save the input text because we have thousands and thousands of gigs of stuff that we can try to save. We don't need to. So we can reliably repeat it each time. Here, if you like color things and lots of little arrows pointing in different directions, you can see kind of what happens here. You go from these code compliant models to all these templates. You have the building parameters that come in from another place, and you have climates that come in from somewhere else. You put them all together into this file, and you generate this is the design day file. So you run the simulator to get this system set right for sizing, run it again for the annual run, and then out comes all the stuff that we actually do that I showed you, where we calculate what the results are. It takes, even with our fast computers, it may take a solid day and a half computing time to do this. Now we speed it up. It would take a lot more than that, but we farm them out on the system. We found that if you went and found a computer on the system at the lab, and you could send it out there if it was empty for a moment, it wasn't being used like that. We have a queuer thing that goes, that one's empty, so it sends the thing over there and then grabs it back. So you never know really where they're all going on at one time. They're all happening. Sometimes they're happening parallel, sometimes they're in series. If the guys that are simulating the climate models that they're running and stuff, you can go slow because they take all the computing power. But when they're sleeping, we're humping. So, next slide. I want to put this slide in. I hope you guys, well, they have copies of the presentations on those old memories.
Yeah.
Okay. We tried to put some of the references for some of these places where you can get information if you want to go find it. I don't want to cover a lot of them, but this is the CBEX is the Commercial Building Energy Consumption Survey that we use to describe a lot of the buildings. The Advanced Energy Design Guides, which are a series of documents from ASHRAE. By the way, ASHRAE doesn't always give things away free, but Advanced Energy Design Guides are free. You can go to the website, you can download every single one of them free. If you didn't know that, go do it. Go do it. We have 30% guides, we have 50% savings guides. Just to show you that I got eternally stupid from doing the 99 standard of 90.1 before I got to the presidency. I chaired the first committee that wrote the first Advanced Energy Design Guide and then hung around for a couple more before I could extract myself. So when I say I'm eternally stupid, I'm really serious about that. There's some previous research and studies that are around, and then of course at the end of the day, you got these expert people that are sitting on the committee that kind of help you make those decisions. Finally, you just don't have any more data, and now you got to go with the judgment of the people. So there's a big human element in this, but we've got most of the rest of it kind of done in a proceduralized way. And again, a lot of this can be replicated on a much smaller scale for people in other places. We've got a lot of diversity. All of the climates that we have, let's go to the next slide. Maybe I don't remember if the climates are coming up. No, the prototype buildings. That'll be good. These are the prototype buildings. They're fairly simply described. One of the things, if you've been a modeler for a long time, it doesn't have to look exactly like that building. What it has to have is the same basic characteristic, the same wall area in that orientation, the same window area with the same relative overhangs. You don't need to build it with the real stuff. You just need to have the same thermal characteristics so that it works. And so these were all developed. You'll see some of them of what we call the ribbon windows, which are characteristic of a lot of our smaller buildings, and then you'll see what we call punched windows, characteristic generally of some of the larger buildings. But then here's one with ribbon windows all the way up. And you can see it. Somebody said nobody builds a building like that. I've got some pictures of a building that looks just like that. I got a picture of one that looks just like this too. We've actually found them in there. So we sent people out all over the United States and said, find us a building that looks pretty close, just take a picture of it. So when somebody says nobody builds a building like that, we have a picture of it. So if you like pictures, I keep pressing this. You have the finger. Okay. This is not meant for you to memorize everything on here. It's just meant to give you a summary of the prototype building that is used. So we actually simulate 3 office buildings. And here you see the floor area. You know, one of these days I'm going to get this over in the SI units, but I'm an old dog. It's hard to teach old dog new tricks. I grew up in the other system of units, and I don't know when to. If I go to SI units, I can't look at it and tell whether I got the right number, so I have to go back and calculate it. So it takes me a long time to change these things myself. So I apologize for that. We should be doing it, but that's just because I'm old and I can't do it myself. So there. Here's the number of floors in the buildings. Here's the heating systems, the cooling systems. What is primary here? Constant air volume, variable air volume, so on. And then if they have secondary systems like education does, healthcare tends to have it in some cases, and some of the logic depending on where you are. So this was a bunch of expert decisions. We sat down and we looked at what we knew was going in out there, and we just made those decisions. Okay. We're trying to, as best we can, represent this broad spectrum of buildings. Next one. Here are the climate zones. I want to say a few words about this, and there's something that isn't on this slide, but it'll be on the next one, that you'll at least be happy about, because we got a climate zone that's unique over here in the Middle East. So every time that the standard was written before, the committee would always sit down and they would choose different buildings and stuff. We got rid of all that. They do all sorts of things. But the other thing they used to do is they would decide, for some reason, that committee decided that there needed to be more or less climate zones. for a whole variety of reasons. They thought it was unfair. And finally we said, wait a minute, why can't we standardize on something? So there was a multi-year study that was done where we gathered data from every location in the world that had long-term equivalent data. Long-term, like multiple years. You don't want a year, you want a bunch of them so that you can get a sense of what the longer-term trends are. We gathered that data from every place in the world that we could. And then that research project went out and tried to establish the climate zones. And the climate zones are described primarily by what we call heating and cooling degree days. And then, of course, because humidity has a play in this, we have an overlay of humidity zones on here. So having said that, now let me try to explain some of this. By the way, all these little lines in here, this is, you recognize the United States, I hope. This is all these little lines in here. These are county boundaries. And the reason we do that is, at least in the United States, we only change things when you go to another county boundary. Everything lines up on a county boundary, because that's where the rules and regulations are made. And you don't have a county where they have a different rule in the northern part of the county and the southern part of the county. It just doesn't work that way. The governments set these things. So those are just the lines that define the county boundaries. The colors are the colors of the climate zones going from the south up to the north. It gets colder, obviously, in the United States in the north and warmer in the south. You'll see here, I'm going to call your attention here. Here's one of the climate zones here, climate 1, which would have been ostensibly the warmest, hottest one. We have only some of the islands within the continental or within the United States. This is all we've got in here. But there's another location in here. Riyadh will be it. It's one of the hottest. And so there, you'll see in the next one that we've got Riyadh in here. So Riyadh falls into that range. But then you have this issue where we had areas which are moist, a lot of humidity, or relatively a lot of humidity, and then we had areas that are dry. So in the United States, the east is more humid, the west is drier. I live in the desert. I got to show you where I live. You can't do this. Out there, I can't hold it that still, but I'm right down in that corner out there, and I live in the desert. Everybody, you'd say Washington, they say Seattle, rain. I go, Tri-Cities, desert. We are drier than Phoenix, Arizona. And we produce all the food in Washington. And how do we do it? If we didn't have rivers, we'd be dead. We don't get any rainfall at all, hardly. Very little. I came from Florida to Washington. I had an umbrella. You always took a rain. If you lived in the Gulf South anywhere, you always take an umbrella with you every day to class because you're going to get rain. Okay? I carried the umbrella around at the lab for a year and a half, finally threw it away. Didn't rain. It never rained when I had to use the umbrella, so I just gave it up. So we have moist properties primarily here, dry out here in the west. It's all very arid pretty much. And then there's this thing called a marine climate. When they looked at it globally, what you found was things like in the Mediterranean, you have these kind of climates that are somewhere in between, right? There's some moisture there, but it's not like the dripping humidity all the time, but you get the right kind of moisture. It's a little cooler sometimes and those types of things. And so those were the three things that get overlaid over that. You have temperature, and then you have the moisture that you overlay on it. And that's how we actually came up with all the climate zones. Next slide, please. There are the representative cities for each of these climate zones. You pick one that's a representative, and that's what you simulate on. So there's Riyadh. There's the hot, dry. Miami's hot, humid, of course. If you've ever been down there. And then you go along the Gulf Coast, you find hot humids, and sometimes you find some kind of warm humid. This is not on the coast, of course. Memphis is roughly halfway up. But you end up with that. You see humids in one, dry in the other, and some of them have marine climates like Salem, Oregon, and things like that.
How come Nevada is also dry?
So which one are they?
Nevada.
Help me find it. It's not there? Oh no. Well, let me tell you how we picked it. We had to pick one We wanted to pick one climate that was representative of that. And we, I don't know, it's a cluster analysis. If you've ever done cluster analysis where you try to define, you know, something is either close together or not close together type thing, we looked for the most representative climate, that if we did that one, we felt that it represented that whole cluster there. And that's how we did it. It was all done scientifically. The guys that were doing it didn't actually even know what the locations were. They just said the location, you know, X, and the cluster analysis will show you really quickly which one, what cluster analysis basically tells you is if you run this one right here, you can adequately represent this other group here because there's a whole bunch of locations that are close to it, close enough. All right? I don't want to go into all the statistics. Do we have any statistics majors in here? I took a lot of courses in statistics. I took the first class about 3 times trying to understand it. I think I took the second class twice trying to understand it. They had the worst nomenclature I've ever seen in my entire life. And we had statisticians in the lab, and I didn't understand what they said either. So. Okay, so that's how we did it. Let's move along here. Here's just for your information, there's some data here if you want to take this stuff with you. This is the breakdown of each of the prototype buildings, and then this is the construction weight. What that means is that this contributes 2.66% to the final answer. So you get the simulation answer for a large office, and we weigh them all together to figure out what the total number is. We don't just add up all the locations, we add them up in a weighted basis. We had to go out and spend a king's ransom to buy some data from one of the companies that sells this data on here that comes out with permits like that. And it took us forever to analyze this. And here, it's kind of hard to read on here, but I think when you look at it on your slides, when you pull it up there, this is the report that described where we got all this stuff and how that was done. The reason we're giving you a lot of this information is if you choose to do something like this, here's the processes we use. And you can use those processes in your area, your country, whatever it is that you're looking at. Okay, next slide. Here's the final progress indicator. This is the last one we did. The final was at 153 addenda. I think we showed that on the previous slide. I want to just mention here that addenda don't always have energy savings. Some of them change things for a reasonable purpose, but they don't result in energy savings. Most of the ones that do happen in these sections 5 through 10 of the standard, the earlier ones are a lot of administrative and definitional and stuff like that, so you change it, but it doesn't have an energy impact. There was only about 72 of these that actually had energy impacts, and of those 72, there's only 53 that we were able to quantify those things. There are some things you know they're saving energy, but it's just very difficult in the simulation to quantify. Next slide. Here's one of these guys, this stacked bar graph here thing. I don't want you to try to read that thing really close. But as you go across, it's climate zones going across. The 2 bars, each one side by side, represent one of the locations, and this little yellow block just shows you how much the savings were in the different locations. And the parts of the stack bar are the energy savings from the various components up here. You might look at a couple of those just to see, this happens to be the school use, and you can see what's happening, where we're saving the most energy here in the schools. So you get a sense of this. Next slide. I think this is one with another set. This one is the fast food restaurants. I want to point out something here. First of all, they use a lot more. The bars are taller. They actually use a lot more energy. You can save a lot less energy in some of these buildings because where they're using the energy is hard for us to get savings. And the bulk of their energy savings is either in refrigeration or it's in the fan energy and everything else to keep these things ventilated. That's where they eat all the stuff up. So it doesn't make what you put in the walls for insulation really makes almost no difference. What you do in this other place makes all the difference in the world, whereas the school will be very different in that regard. Okay. There's the energy savings. The other one had a couple of examples where you had the bar charts. Here you can actually come and look at the energy savings. We do energy savings in 2 things: the site energy, which is where the meter is, and energy cost savings. And we look at both of those numbers here. And we always calculate the national average. Next slide. I think we're almost done here. here's kind of the final result of all of the things. There's the fast food and the sit-down restaurants. They have the highest DUIs, like substantially. I mean, hospitals, you think hospitals are energy intensive, but those little buildings there do. So, note to file, don't build any more of these. Okay. Do something different. Can't afford too many of these. Next slide. Here's the final ones with everything adjusted without the plug loads, the things that we can control. So we made the 30% savings both in energy cost as well as energy site savings. So we made the target, cleared the bar just barely, but we did. Next slide. That's just a quick summary of what we had. Go on to the next, if you would, please. I'm not sure why I had that slide in. All right. Thank you. I knew there was something. Why did I put that last one in? Real quick trip, how you do it, okay? But there's things in there that you can take away from this if you want to do something in your area. The framework of what we've laid out is a workable framework. It actually is. I'm showing it at the most complex level that it can be done, so you can understand the effort. But does anybody have any questions? Yes, then you.
Well, you said, it's one question regarding the 30%. You said that DOE said 30%, right? When the government, even here in UAE, it's 2020, they have 20%. Same in Saudi, they have, the government looks at what exactly when they
looked at, the one that they actually looked at was that final one you saw there where it had two columns. We had energy cost savings and actually site energy savings. They looked at those totals right there. And one of those was like 30.1%, the other one was 32 or something. The energy cost savings and the energy savings can differ because the energy savings is measured at the meter, and particularly when you have buildings that are mixed fuel, like we have gas and electric in there. If you just look at the meters there and you add that stuff up, you got to convert the BTUs and the fuel to that, so you get a different answer than the energy cost. But interestingly enough, in the U.S., those numbers were not that far apart, if you remember. They're pretty close. And that's because if you look at the actual average price of gas and the average price of electricity in the United States across the country, amazingly, they're just about the difference between the site source values of the energy. But what that means is that the economy actually works. It reflects what the real value of it is in the price. Okay.
And what you actually said exactly, what you looked the first, like what was your first priority? Will you save like 10% from ventilation, or what parameters you were looking at?
Well, actually, for DOE, what they wanted was the whole standard saved this much. They were looking at those bottom lines. If you go back and look at the details of the progress indicator, we can tell you what we're saving. Remember those bars that stacked?
Yeah.
If you go in there and look at it right there, you can see it.
Okay.
Look, it's hard to read that particular thing on the screen and assimilate it.
Yeah.
You know, I just said to somebody, can you get all of this on one slide? Right? And they did, and then you see how readable it is. That may have been a mistake on my part a number of years ago.
Okay, we'll see.
But that stuff's there. And the reports, everything, those reports, everything about what we did to get there, as well as what the results are all contained in some of those references that you can see online. I mean, that's available. It's widely available. No secrets here. Yes?
Did you consider at one time revisiting the number of climate zones and see its impact on the savings as a whole?
No, the question was, did we consider changing or changing the climate zone to see the impact on there? No, I don't think we wanted to do that. I think because we had done so much work to try to figure out what's the really representative things, to go back and look at it differently and change the climate zones is to open the door for the next committee coming along to start messing with those climate zones and undo this work. The great value in a lot of these things is to find a good baseline and a metric to use and continue to use that thing, even though there might be other things that could be a little better at some point in time. Because as soon as people start changing it, you no longer can compare it to the stuff that happened in the past. And that was what was happening before. The savings from the standards were simply not comparable. We couldn't rationalize any of it. So if you look at, I don't know if all countries use something like this, but in the U.S. we have something called the Consumer Price Index. Okay? Do you know what the baseline for the Consumer Price Index is? It's 1932. Nobody's changed it since then, because that's what it was then, and that we always compare back to that. And that way you always know where you are in that long string of things. The minute you change the baseline, all the rest of the data is not comparable, and you've lost the thing. As much as the tendency is to want to change those things, right? Don't do it. It's a headache. It took us years to understand that. It really did. Okay, other questions? None. So it's coffee break now, I hope, or something.
No, we have the technical.
Oh, no, we got another one?
We have the technical session.
Oh, we do. It's in here right now? Okay, good.
Thank you, Ron.
I can sit down, somebody else got to talk.
for the rooms. That dictates also how much airflow we might need. And finally, we have this dilution or minimum ventilation requirement. Now, typically, whichever of these is highest is going to drive the airflow in the room. So it's not the average, it's not the sum of them, it's really whatever is the highest specific requirement is what we will need to provide for that laboratory room. So it could be the fumes. If you have a lot of hoods in a room, a high density, then that might be the driver. But typically for most lab rooms, for many lab rooms, it may be the thermal load, but again, typically it's actually this dilution or ventilation requirement. Typically we need to have a certain amount of airflow to always purge through the room to keep the air clean. So if there's contaminants or chemicals in that room, it's going to basically purge them and get them out. So typically we'll need 6 to 8, maybe even as high as 10 or 12 air changes that we run all the time to be able to keep that airflow clean, keep the lab clean. And unfortunately that uses a tremendous amount of energy to basically flush 6 or 10 air changes of air, heat it, cool it, blow through the building and exhaust it. It requires an enormous amount of energy. Typically lab buildings use 5 to 10 times the energy use of an office building. So this is a huge issue, and it's related to these factors. So the key is that, as I said, typically we can focus on these. If the thermal load in a room is high, if we have a lot of cooling requirements, we can usually decouple that from the airflow by using like a fan coil unit, or you see now more the use of chill beam technology, which is like cooling coil in the ceiling, basically a non-condensing cooling coil. So these are approaches you can do to decouple the airflow, and at that point, if I can decouple it, so now the airflow is not based on the cooling, I don't have as many fumes, or I can keep the sashes down, then it's all about the ventilation requirement. So how can I get that down? Because that's really going to be the driver for most of the energy use. So the key then is to think about, well, why do I have that airflow? And typically the reason I have it is because I need to keep the air clean. It's an air quality issue. That's what we're focusing on. But what we find is that most of the time the air in the lab is actually clean. Turns out 98 to 99% of the time the air in the research lab is actually as clean as it is in this room, which is pretty clean. So the key then is that I'm basically wasting a tremendous amount of airflow. The analogy I would give you would be up here in the ceiling. You see over here in the ceiling we've got these sprinkler heads. It's a great invention. Basically it's a water on demand. When there's a fire, those devices effectively sense the fire and they release water, basically providing water to put out the fire. It's a great concept. But what if we hadn't invented that yet? We didn't know as a society how to control water based on fire. We didn't know how to sense the fire and turn on the little valves there to provide the water into this room. What would we do if we want to protect this room? One approach might seem a bit crazy would be, why don't we just run water flow all the time? That way, if there's a fire, the water will put out the fire. It's a great way. It's guaranteed to work. So we could do that, and it might seem a bit crazy, but it wouldn't have floor drains. It would be, we'd cycle the water. Would basically be sustainable. Would have our little umbrellas we'd carry around. Would have advertising umbrellas. Would make money. It'd be great. It would boost the economy. It would be terrific. And we think that's normal for a commercial building. We always have water flow all the time. But as crazy, again, as that sounds, that's exactly what we do in laboratory buildings, not with water flow, but with airflow. We just can't see the air, but it's obviously coming down in this enormous quantity that is used all the time. And again, sometimes we need it, but only about 1 or 2% of the time. So the question then is, how could I then control, like the sprinkler head, how could I then provide water flow, or really in this case, airflow, on demand? So the approach then, what we want to do is actually sense for the contaminants, because that's what we're concerned about. That's why we have the airflow. So basically what we want to do is sense for the contaminants. If we see there's contaminants and pollutants in the room, then we want to provide actually more airflow than we normally would. Instead of 6 air changes or 8, if we can, let's go to 8 or 10 or even 15 air changes. Sort of that range between 8 and 15, which gives us a very good purge of those contaminants. But if the air is clean, then let's go even lower. Let's go down maybe to 2 or 3 or 4 air changes and save energy, because we don't need that airflow. It's only there for getting rid of contaminants. So if the air is clean, why dilute clean air with clean air? So this is a very simple concept. More airflow when you need it, less airflow when you don't. So now the question is, how do I sense those contaminants? Because typically we want to sense a variety of things. Some chemical contaminants, maybe particulates like smoke, maybe carbon dioxide. If there's a lot of people in the space, you still need people ventilation too. So how do we sense all these parameters and do this cost effectively and also at the same time reliably over time? Well, there's different ways obviously you might think of doing this, but basically I began thinking about this issue many years ago and said, well, normally we take a sensor and we put it in the environment, we put it in the room on the wall. But my thought was maybe we should do exactly the opposite. What if we took the environment to the sensor, took a sample of air from many different spaces, sequentially back to one set of sensors? It's something that I call multiplex sensing, basically an air sampling system. And these systems have been around for many years. They've been used for carbon monoxide. There's different ways you can implement them, but the concept is the same. You use one set of sensors to sense the area or the volume within many different areas or rooms. what we're going to do is basically get a sample of air sequentially from each space, one after another, so I can use basically one set of sensors to measure maybe 20 or even 30 different rooms. So now we have a much more cost-effective approach. You can sort of see this concept in this little animation. So here's a little vacuum pump. We use these devices called routers to basically switch the airflow onto this backbone. So we have little samples of air coming down, one after another. There's little tubes basically that are set through the building. A very simple approach, basically again, a sampling concept. Now, one of the advantages beyond just the cost and the fact that I don't have that many sensors to calibrate is another very, very powerful advantage of this type of system. And it's the issue is that all sensors, typically gas sensors like a VOC sensor, volatile organic compound sensor, sensors like that, or carbon counters, or carbon dioxide sensors, even those sensors, they tend to drift over time. That's a huge issue. We'll talk briefly about this later. So the question is, how can I eliminate this drift? If the sensor is always drifting, I'm going to have inaccurate results, and I'm not going to be able to save energy. However, if you look at this concept, I'm using the same sensor to look at the outside air as the inside air. Now, I always want to look at the differential. Whether it's carbon dioxide sensing for demand control ventilation, or in this case, a laboratory, I can't do anything about the outside air. The outside air has contaminants, it has particulates. It's going to come into this room. I can't do anything about that. But what I want to control is what's in the room. I want to get rid of the contaminants that are in that space. So what I care about is not the absolute level of particles or vapors. It's the difference from what goes in to what goes out, because that's what I'm creating inside the room. And that's what I can dilute by the fresh air from the supply. So what we want to do is look at the difference between the supply and the exhaust. That's how we want to control. But once I've done that, if I use different sensors, if I have a sensor here and then a different sensor here, then I'm going to have different errors. Some sensors will go high, some will go low, and it can create quite a significant accuracy issue with respect to that measurement. However, if I use the same sensor, which is located here, and I make a measurement of the outside air, or supply air, and then a few minutes later I make a measurement of the indoor air in this room with the same sensor, the offset of that sensor is not going to change. That drift is going to be the same within a few minutes. So now, let's say the sensor is off by 100 ppm, it will be high by 100 ppm here, high by 100 ppm here. If I take the difference, that 100 ppm cancels out. So now I get a very accurate result. So this idea of a multiplex or air sampling system with a common sensor provides very accurate differential measurements, which is what we need to control the building and save energy. So this is one of the advantages of this concept. So this is sort of the approach now. The question is, how well is this working out? What has been done? Is this recommended by ASHRAE? Well, this concept is included in the ASHRAE handbook now. The lab design guide will have it as well, and the upcoming version will be coming out in about a year. But it's also in the lab chapter of the ASHRAE applications handbook. So basically what you're seeing here is it's referred to as real-time sensing of contaminants, provides a way to save energy in labs, and again, allows you to go safely down as low as 2 air changes per hour when the lab air is clean, versus a normal level 6 or 8 level, which would be much higher. So let me give you some examples of where this has been used. One example is the Arizona State University project. This is again, I mentioned before, was a LEED platinum building. And then basically this concept was applied to it and reduced the energy by about $1 million a year. You can sort of see this was where they were running. They're actually running about 12 air changes with this lab, pretty high. But they were doing that to try to be safe with respect to the facility. But then this was able to be reduced down to 4. Again, little things are happening. Some rooms may be going high to encourage some contaminants. Maybe there's some fume hoods that are going high. But you can see that the average reduction in airflow is quite significant, almost a factor of 3 to 1. So this is why they're able to cut the airflows so significantly and cut the energy by over $1 million a year in this project. Another example is the University of California, Irvine. Talking about energy targets, I think last we were talking about, Ron was talking about cutting like 20%. I mean, in the U.S. we have the Better Buildings Challenge. This is a challenge by Obama to basically cut the U.S.'s energy consumption by 20% by the year 2020. So he's challenged institutions, universities, corporations to cut their total energy use by 20% by the year 2020. The first university in the U.S. to hit that target, and they did it in 2013, was the University of California, Irvine. And they achieved it by basically reducing the energy use in their laboratories, and the prime driver for that was this concept, this approach. So this is an example of how they applied it. This was one building that was done before, built in 2001, was recommissioned in 2010, to beat their energy code in California, what's called Title 24, by 24%. So it was a good building to begin with. But then they applied this concept of demand-based control to it, applied it going from 6 air changes down to 4 during the day and 2 at night, sort of 4 occupied, 2 unoccupied, and reduced the energy now by 50%. So very significant increase in energy. Here you can see the reduction in energy use. Here's what it was before in the older building. Here's the newer building. Obviously very significant reduction in energy per square foot, or technically per square meter. This is also the HVAC energy, the pump and fan power. This is the other building, the older building with the fixed airflows. And this is now the variable approach, the demand approach, obviously much less. So this is a summary of what they achieved. This is how they hit the Better Buildings Challenge, because they took these lab buildings that were running anywhere from 6 to as much as 11 air changes. They were different levels. The average was about 8 air changes of airflow through that facility. And then some were constant volume buildings, some were already variable volume, but didn't use the demand-based approach. They converted them all to variable volume and then using demand-based control. And these are now the kilowatt-hour savings that those buildings achieved. So very significant, average about 55%. And then there's also the heating savings, which is basically reheat. Southern California, pretty mild climate, but a lot of reheat energy, and that was reduced very significantly. Now there were other things they used. This is what they call their smart labs retrofit. It had some lighting changes and a few other things, but the bulk of the savings, at least a half to 2/3 of it, or 3/4, was this concept of demand-based control. That's again how they achieved the Better Buildings Challenge goal of a 20% reduction. They've actually upped and said, we'll do not just 20%, because we've already hit that. We're going to go for 40% by the year 2020. That's their aggressive goal, so they're hoping to do even more. Other facilities that are using this, again, it's a common approach. It's used in many lab buildings, so again, it's been very successfully applied over the last probably 10 years. So let me give you an example here in Beirut. So let's say, what can this do in a laboratory that's located here in the city? So I've basically taken the weather climate for Beirut and basically applied it to a lab building that had about 12,500 gross square meters, of which labs are about 5,000 square meters. And basically what we have is a dilution of a baseline of about 6 air changes. I've got some energy costs here, and then basically normal set point temperatures. So when we apply that, the base cost of using the 6 air changes runs at about $615,000 per year. You can see how that breaks down between cooling, a little bit of heating, some reheat, and then some fan power. We then apply the demand-based approach to that to bring it down to 4 during the day, 2 at night. That's roughly about half the flow, or about roughly an average of 3 versus the 6. So here is the baseline, and now here's the new energy use, obviously less than half, about 53% reduction, and a payback in this case was around 1.6 years. So again, very significant reduction, again, because we can reduce that airflow rate. Okay. Lastly, I just want to briefly talk about demand control ventilation in commercial buildings. When we talk about laboratories, what about in commercial buildings? The concept, again, is called demand control ventilation. It's been around for a long time. You've probably heard of it, or hopefully maybe heard of it. It's recommended by ASHRAE. ASHRAE 62.1 specifically recommends this approach in the code, in the standard, I mean. And the problem is it hasn't worked that well, I hate to say. And there's been some articles talking about this. The problem is that the traditional sensors that are used tend to drift, as I mentioned earlier. This is a study that was done by Lawrence Berkeley National Labs, showing that out of 44 sensors they surveyed in the San Francisco Bay Area where they're located. Again, they're a Department of Energy laboratory. And they looked at this and they found that the far majority, about 80% of the sensors, were drifting high by almost 40%. These sensors should be accurate at 3 to 5%, but they were obviously significantly higher than they should be. And if you think about that, if the sensor thinks there's more CO2 in the room, it thinks there's more people in the room, and it drives more flow. So the result of that is if you look at each of those sensors and apply them into a demand control ventilation system to vary the airflow based on the CO2, it's going to think there's more CO2, it thinks there's more people, and it drives the flow higher. So a few of the sensors were reading negative, that would reduce the flow, but about a quarter would be reasonably close, within 20%. But again, almost 2/3 of them are reading much higher. So the average is about 180% high. So that means if it should be 10,000 liters per second of airflow, it's really going to be more like 28,000. So it's almost 3 times the airflow. So in reality, these systems aren't saving energy, they're actually wasting energy. It's part of the reason why you hear this backlash against green buildings, where people are saying, green buildings aren't saving me energy. My bills went up, what happened? And it's for many reasons, but one of the reasons is these sensors. The issues, the sensors are drifting, they're not able to be maintained well, and the result is a problem. Now some people have said, well maybe if I just did do the maintenance better, that would solve the problem. So people have talked about, oops, I didn't have it here, but people talk about using looking at new sensors, and there were some studies also done on new sensors that also showed similar levels of drift. So it's not just a maintenance issue, it also is inherently the way these sensors unfortunately work. However, as I mentioned earlier, if we use that concept of this differential measurement, the idea of using a single sensor, an air sampling system concept, then that is going to cancel that drift. So again, whether it's a laboratory or whether it's a commercial building, we can use the CO2 sensors, and we can use them accurately by using this concept of canceling the drift by using a differential measurement with the same sensor, with an air measurement or air sampling system. So the result of that is we can get good accuracy by using these approaches where this differential accuracy will help. One sensor then cancels the drift, so that's a good approach. The other thing I mentioned briefly was the idea of a healthier DCV. The problem is that with demand control ventilation, we're just looking at people, just looking at CO2. But sometimes there's other contaminants in the room, the non-human contaminants that we talk about sometimes, that can create problems as well. So again, one approach is to sense the other parameters, like we do in laboratories. Sense the volatile organic components, sense particulates, like we do in the lab. And that allows us to look for those areas that might create an unhealthy situation. And then we can increase the airflow based on that. So that creates a healthier approach to it. A little more expensive, but it provides a better indoor environment. So there's basically we have some options for how to control the room, either based just on CO2, which is more related to people, or we can provide some other parameters and then provide a healthier environment that looks at all the other areas as well. So that's sort of the concept of what we can do. Just a quick example, so this was applied in a project at the Bank of America Tower in New York City. It's a large, about 200,000 square meter project, sensing over 800 locations, again, to provide a better indoor environment as well as a more energy efficient facility. ASHRAE headquarters is using the concept as well, so again, it's been recommended in some of the different handbooks, and then they applied it within the facility also. And lastly, I mentioned the Apple headquarters, again, very interesting project here. I think Steve Jobs wanted a building so large you could see it from outer space. So I'm not sure if that's an ego issue or whatever, but the bottom line is he and Norman Foster put together this massive plan that they're now implementing in California. Really about 1.6 kilometers around this, basically a whole mile around that ring. Really almost 300,000 square meters. What I thought was interesting about this project is that Apple is so paranoid about security. I mean, they're worried the next iPhone 7 is going to be leaked to the press. So they wanted to make sure there were no service people that ever had to go into the occupied areas, into the office areas. So they wanted no service whatsoever in those areas, which is difficult. You have to put sensors in the spaces. But the concept we're just talking about is an air sampling approach where all the sensors are remote. They're basically sitting in a mechanical area. So it meant that there was no sensors in the rooms, just pickup points where the air is being pulled out of the room, and the sensors then located in a mechanical area. So they really liked that approach because it meant they didn't have to have any service people go into the occupied areas. So again, that was sort of an interesting approach that Apple liked. So bottom line, just to summarize, what we're saying here is that this concept of a low air change airflow design for labs is a way to significantly reduce the energy consumption of these facilities because it's what airflow is what drives the energy use. Again, so the biggest impact then is this band-based concept because we can reduce the airflows by a factor of 2 or 3. And lastly, again, keep this in mind as well for normal demand control because it also allows us to keep the sensors, cancel the error of the sensors and get an accurate result so we can get energy savings more precisely, more reliably. So with that, any quick questions maybe to summarize? Questions on the presentation?
Any questions?
Gordon, you said can it be retrofit also for retrofit projects? I saw a couple of examples.
Yeah, I mean these concepts of demand control and demand-based control can be very easily retrofitted in existing facilities. So yeah, this is not a problem. So a lot of people like what I mentioned before, the University of California, Irvine, those projects were all retrofit projects. So they were basically trying to cut their energy by going back to the existing buildings, which is obviously where the largest amount of energy use is. It's not the new buildings, it's the existing ones.
My question is that in cases of this controller for the CO2 sensing and the air pollution and BPM, in case of the minimize outdoor air ventilation, what about the verification of the set point temperature for the thermal load interval?
So you're asking about how do we verify we're getting enough air cooling or air conditioning within the space?
Yeah, how to verify that when we're minimizing this fresh air due to the lower level of BPM or CO2 or something like that, how could we verify that the set point temperature for the occupation is achieved?
Right, so basically what the question is, if I got it right, is basically how do we, if we're going to reduce the outside air pressure, how do we maintain or ensure or verify that we're going to get the proper temperature control within the space? I think this is, what you're asking. And the reason that, again, it goes back to what I mentioned before. When you look at the airflow requirements, let's say for a laboratory, it's higher of either the temperature requirements or the air change requirements or that the fume hood. So the key is that whatever is higher will dictate. So just like a thermostat looks at temperature and it says, it's hot in here, I need more airflow, we're doing the same thing with the contaminants. If it's contaminants a problem, then obviously we provide more airflow as well. Typically those systems have a reheat or a reheat approach, so if it's more airflow because the hoods are open or because there's a requirement for air changes, then you'll have a reheat control as well. So the temperature control typically in these systems is always separate. It's always operating independently by varying the amount of either reheat or the airflow to make sure it works. What we're doing is allowing the minimum to go down because typically these rooms are overcooled and that results in then more energy use. But if we can reduce the airflow, then obviously it will save energy, but then the temperature control still operates as needed to provide more flow when needed. In a commercial building, typically we're just varying the outside air, so we're not varying the supply air, so it's not affecting the temperature control. All we're doing is varying the amount of outside versus return air, that mixture. So that doesn't affect, again, the temperature control. So it's still, we can monitor the temperature, verify it's still working correctly. Other questions?
Sorry?
Yeah, in the back.
When going into VAV technology in the labs, what is the air valve technology used? Is it a Venturi or a VAV with a motorized damper?
Right, so the question is when we start applying this approach we're talking about basically relies on a foundation technology which is variable volume technology. So obviously we need to vary the airflow, so we need to place some type of a system to do that. Now, Venturi valves, that's the technology that I invented back, at Phoenix Control, so I'm happy to have you, that's great technology, there's nothing wrong with that. But there's other technologies like VAV boxes and other technologies that can be used as well. This concept really works with any of them, so it doesn't really, these are two separate approaches. One is we need to have a system that varies the airflow, whether it's valves or VAV boxes. Obviously it doesn't really matter as long as it controls correctly. This concept then acts on top of that as a separate system that's really giving information to that VAV system to make it more efficient, to operate it more smartly and more intelligently. So
but the energy varies between the two systems.
Say again?
But also the energy varies between the two systems. If you're using an air valve or is using the damper. Because we see always the air valve for the constant air volume technology, not with the VAV. Those VAV valves can be used for variable volume as well. So the question then really relates to that when you're going to use variable volume, because obviously a system like this requires the airflow to be reduced. So that's the way we're going to get the savings. So we need a system that's there to reduce flow, maybe related to the fume hoods, maybe to the temperature, and then this is added on top of that. But base technology is some sort of variable approach. There are Venturi valves that allow you to vary. There's some that are constant. So here you want to use the ones that are variable. Just like you want to use a variable VAV box or variable air volume box technology as well. So as I said, there's a variety of manufacturers and systems out there. Obviously, we don't want to get into the names out here, but basically there's a variety of technologies out there that in systems that are on the market commercially that vary the airflow rates in laboratories to maintain pressurization as well as to provide a safe environment and vary the flow rate. So this concept here fits on top of any of those. It doesn't matter, and it then allows you to save more energy because it reduces the flow further than they would normally be able to do. They would only get down to 6 air changes. Here we're going to bring it down to like 2 or 3 to reduce the airflows and save even more energy.
All right. I have a question.
Sure.
Would the location of the sensor that senses the CO2 concentration, would it affect the operation of the airflow?
Right. So good question. So the question is, does the location of the CO2 sensor affect how the system operates? And it turns out carbon dioxide is a gas that disperses and diffuses quite easily. So whether it's on the ceiling or whether it's on the wall is really not going to make much impact because the CO2 will diffuse out pretty evenly well distributed with normal air currents in a room. So it's not too critical where that location is. I know, LEED is an example. I mean, the LEED, the USGBC, the LEED system, when they talk about using demand control, they like to put it on the wall. I mean, their preference is to put it in the breathing zone. But frankly, it really doesn't make a lot of difference. I mean, that's their preference, but I don't. My personal experience, I haven't seen much of a difference in the operation, whether it's on the wall, up in the exhaust duct, where the air is going out or return.
All right. Thank you.
Thank you very much.
All right. Okay. Our next speaker is Karen Habshi. Let me introduce Ms. Karen Habshi. Her presentation title is A Simplified Mathematical Model for Predicting Cross-Contamination in Office Building Air Conditioned by Displacement Ventilation. Ms. Karen Habshi graduated from the Lebanese University with a master's degree in mechanical engineering. Currently, she is pursuing her PhD studies at the American University of Beirut. The aim of her research is to enhance indoor air quality and thermal comfort of occupants in indoor spaces by the proper design of the HVAC system. Her work involves numerical modeling, safety simulations, and experimentation.
The current session will present a modeling approach.
Can you raise your voice? You prefer to sit down here. Can you raise your voice?
You either have to raise your voice or get the microphone.
A simplified mathematical model for predicting cross-contamination in office building air conditioned by displacement ventilation will be presented. People spend the majority of their time in indoors environments. For this reason, the occupied space should be comfortable and healthy. Therefore, the air conditioning system should be properly designed to ensure good indoor air quality. Displacement ventilation systems are a ventilation technique that is widely used in office spaces and buildings for its effectiveness in providing good indoor air quality and ability of transporting contaminants to the upward level. DV system relies on rising surface flow due to buoyancy effect. In these systems, air is supplied at low level and exhausted from the ceiling. Displacement ventilation results in stratification in temperature, where the temperature is cool and is warm as we rise up. Concerning the concentration variation with height is widely dependent on the relation between contaminant and heat sources. Usually, contaminated sources are at the same time heated sources. So, the upward rising flow will transport the contaminant upward, increasing the effectiveness of the displacement ventilation in removing contamination. The objective of this work is to reduce cross-contamination between occupants in typical office space by developing a simplified model that can predict particle behavior within the space. Particles can be divided into two categories, passive and active particles. Passive particles are particles that have a density similar to the air one, so that they will be carried by the flow field. On the other hand, active particles are denser than the air, so the gravitational effect and the position on the walls will affect their behavior. To ensure indoor air quality, we should not only look at tracer gas at CO2, but also at active particles, which extend from sub-micron to 10 microns particles in diameter. In this work, we will come up with recommendations for the proper design of displacement ventilation in order to ensure good indoor air quality. Occupants are one of the main sources of particles in indoor environment. For this reason, diseases can be transmitted through exhaled droplets by the different respiratory activities. For example, an infected person will generate particles that might distribute within the space and might reach the exposed person, which risks contamination. If the ventilation system is not designed properly, the exposed person will be contaminated, which is not desired. model will predict the temperature, concentration, and velocity field within the space. As the displacement ventilation results in stratification, vertical stratification in temperature and concentration, the space will be discretized vertically into several layers. Three main zones can be defined. The first zone extends from the floor to the stratification height. What we mean by stratification height is the level at which the airflow in the surrounding air is equal to zero. I should note that we will consider the different rising plume due to heat sources as well and internal heat source as infected person and exposed person. The region outside the thermal plume will constitute the surrounding air. Below the stratification height, as the plume rises, they will entrain air from the surrounding air. At the level at which the entrained air equals the supply flow rate, the flow within the surrounding air will be zero. So, below the stratification height, the air in the surrounding air is upward, while above the stratification height, the direction of the airflow in the surrounding air changes in direction and becomes downward. For this reason, we will divide the space into zone 1, where the airflow motion is upward, the zone 2, the airflow motion is downward, and this zone is limited by the stratification height and the critical height, where the critical height is the level at which the plume expands. Due to plume expansion, a recirculation zone is created at the upward level. And so horizontally, we will have lumped region. We will have the region of the thermal plumes and the region of the surrounding air. Up to date, the majority of literature studies on active particle behavior use computational fluid dynamics, which presents the disadvantage of needing a high computational time cost. In order to reduce the computational time cost while capturing the main physics of the problem, a simplified model was developed. Since active particles are considered, the simplified model should implement the gravitational effect and deposition on the wall. In addition, to capture the interaction between the different zones, the main physics of the problem should be modeled. In this slide, we can show the main physical mechanisms affecting particle behavior. The transport within the buoyant plume and surrounding air are driven by convective flow and vertical diffusion. Laterally, interaction between the rising plume and surrounding is driven by lateral diffusion due to concentration gradient between the rising plume and the surrounding, and at the same time by entrainment of air by the rising thermal plume. As we are dealing with active particles, the position on walls and the position on walls will be considered in addition to gravitational effect. The velocity field widely affects particle behavior. For this reason, we should properly model the convective flow within the different regions. We used, in our model, we used empirical relation developed by Jaluria and Mont to predict the rising, the upward flow within the rising plume and the flows within the thermal plume near the walls. A simple mass balance can give us the flow rate in the surrounding air by just doing the summation of the mass flow rate within each layer. The temperature field also affects largely the flow field behavior because the gradient in temperature, as we can see in the first equation, affects the flow rate and the rising flows. In order to resolve for the temperature field, an energy equation is used for each layer of. Now, for each region, we will have a particle mass balance in order to compute the concentration within the region. For example, here, within the surrounding air, we have the following equation. The first term represents the convective flux of particles, where Ca is the concentration within the surrounding air, and Ma is the flow rate within the surrounding air. As I said before, we have upward and downward motion. Below the stratification height, the motion in the surrounding air is upward, while above it is downward. For this reason, you can see the maximum function that is introduced to account for the change in direction of the flow rate. The second term represents the gravitational effect, where Vs is the settling velocity. The third term represents the vertical diffusion within the surrounding air, while the fourth term represents the lateral diffusion between the plume and the surrounding. As we can see, the diffusion term is composed of two terms, the normal diffusion and the turbulent diffusion, because the rising thermal plume have a turbulent behavior. So at the boundary, we will have a turbulent diffusion driving the lateral diffusion between the plume and the surrounding. The fifth, this term represents the entrainment of surrounding air by the rising thermal plume, while the last term represents the deposition of particles on walls, where Vd is the deposition velocity and is modeled using Nazarov approach. Also, within a thermal plume, we should have a mass balance for particle concentration. Similar to the previous equation, all the physics are embedded within the equation. The first term represents the upward convective flow within the rising plume, while the second term represents the settling effect. As the two regions are interacting, we have the same terms in the equation of the surrounding air and in the equation of the plume, where we have here the interactive term due to lateral diffusion, the entrainment term of surrounding air by the plume, and the final term is for contaminated plume, where we have generation of particles. As I said before, we are taking two persons, one infected and one exposed. For the exposed person, no generation of particles takes place within the plume. So the generation term will be zero. However, for the infected person, generation of particles will take place in the first layer of the plume, which will be implemented through the source term. To brief the methodology to solve for this equation, I prepared a small algorithm. We begin by assuming the temperature of wall air and gradient of temperature within the room. This assumption will be used to compute the mass flow rate within the different zones. And the flow rate will be used to solve the energy balances by interaction with a space thermal model. Once we solve for the temperature field, we will update the temperature and the mass flow rate. This procedure will be repeated until convergence is reached. Once the temperature and flow field are stable, we will use them to solve for the mass balance within the different interactive zones. As the different zones interact with each other, the concentration equations are coupled. So for solving for the concentration field, also an iterative process is needed to obtain convergence. The simplified model was used to conduct a parametric study on the effect of particle diameter and flow rate on the particle behavior. Different diameters were considered from 1 to 15 microns to cover the inhalable range. And different supply flow rate of 50, 75, and 100 liters per second were used in a typical office loaded by 40 watt by meter square. To begin with, for the smallest flow rate of 50 liters per second, we can see that we have particle accumulation at low level of 1.1 meters. This is due to the level of the stratification height. For a flow rate of 50 liters per second, the stratification height is just at the breathing level. And as we said, below the stratification, air is upward, while above it, air is downward, which makes the stratification height a critical level where particle accumulates. So, if we want to ensure good indoor air quality for the critical inhalable range, the stratification height should be shifted up. How to shift the stratification height? We should increase the flow rate, because by increasing the flow rate, the quantity entrained by the plume can reach a higher level before reaching the stratification. Thus, for a flow rate of 70 liters per second, as we can see, the stratification height is shifted upward from nearly 1.1 to nearly 1.3, where a peak of concentration is shown. For a flow rate of 75 liters per second, we can see that as the diameter increases, the stratification and concentration created by the displacement ventilation system is weakened because the gravitational effect acts against the upward motion below the stratification height. So the gravitational effect will tend to accumulate particles at lower levels than stratification. For this reason, it's not enough to higher the stratification level to ensure good indoor air quality for the whole critical inhalable range. We should make sure that the gravitational effect is not able to overwhelm the upward motion below the stratification height. For this reason, the flow rate was higher to a level of 100 liters per second, for which, for the whole critical inhalable range below 10 micron, we can see that we have a relatively clean zone below in the occupied zone, while we have a more contaminated zone at the higher level. As we are mainly interested in reducing cross-contamination between occupants, the intake fraction, which is the normalized concentration at the breathing level of the exposed person, was examined. To begin with, for a flow rate of 50 liters per second, you can see that for diameters between 1 and 5 microns, the intake fraction increases with particle diameter. However, for particle diameters larger than 5 microns, the intake fraction becomes to decrease. But why? I just said that when the particle diameter increases, the particles accumulate and the risk of cross-contamination increases. However, we should not forget that gravitational effect can play a positive role if floor deposition can overwhelm the upward motion. However, the positive effect created by floor deposition does not cover the entire inhalable range. Only for particle diameters larger than 5 microns, this effect becomes to be positive. So we cannot use 50 liters per second because the floor deposition can act as a positive role, because for particle diameters lower than 5 microns, the intake fraction is relatively high. So what we should do is to overwhelm the gravitational effect so that the floor deposition will be weakened and the contaminant will be transported upward to be exhausted from the ceiling. Thus, when we higher the flow rate for 75 liters per second, then for 100 liters per second, the intake fraction was decreased because the removal effectiveness of contamination by the displacement ventilation system was strengthened because the upward motion is able of overwhelming the gravitational effect and preventing particles from accumulating in the occupied zone. The following table summarizes the effect of particle diameter and flow rate on particle deposition. In fact, for the same flow rate, for small diameter, Brownian motion and turbulent diffusion play an important role in particle deposition. For this reason, we can see that for small diameters, the percentage of particles deposited on vertical walls is relatively high. When the diameter increases, floor deposition becomes dominant, and the highest percentage of particle deposition is on the floor. When we higher the flow rate, the gravitational effect is weakened. For this reason, we can see that as the flow rate increases, particle deposition decreases, and the removal effectiveness of the displacement ventilation system increases. In conclusion, the gravitational effect was shown to increase with particle diameter, reducing the stratification and concentration created by the displacement ventilation system, and risking of increasing the risk of cross-contamination between the occupants. Thus, for the critical inhalable range, higher gravitational settling accumulates particles within the occupying zone, leading to an increased probability of cross-contamination. Designing the DV system such that the stratification height is just at the breathing level is not good to ensure good indoor air quality for the whole critical inhalable range. For this reason, the stratification height should be shifted upward to a level much higher than the breathing level, up up to a level of 1.4 meter, which requires the increase of the flow rate up to 100 liters per second for a typical office loaded by 40 watt per meter square.
Questions? Yes, Dr. Furi.
Yes, you didn't say how you discretized your space in the room in the XYZ directions, and did you take into account the presence of occupants and furniture?
This model is 2D. Okay? Mainly, the grid, we discretize vertically into many layers, but horizontally into lumped regions. Please can I go back to the schema?
Fine.
Our model is two-dimensional. Okay? And that as stratification is mainly in the vertical direction, I discretized the space into a high number, approximately, let's say, 20 layers in the vertical direction, with 3 main zones. In the horizontal direction, I considered lumped region. What I mean by lumped region, for example, I have an infected person having a rising thermal plume. The first, horizontally, I have the region of the infected rising plume, the exposed rising plume, region 1, region 2, the wall plume is region 3, while the surrounding area at the same level is region 4. And within the equation, I take into consideration in the horizontal direction interaction between the different regions. For example, I have here an equation for the concentration within the plume of the infected person. The phenomena are the lateral diffusion and entrainment of air by this rising thermal plume from the surrounding air. At the same time, we have the gravitation, the vertical buoyant flow and vertical diffusion, in addition to gravitational effect. In each region, all these physics are modeled, and the equations are coupled together to solve for the concentration within the infected plume, the concentration within the exposed plume, and the concentration within the surrounding air. Concerning furniture, it's true that furniture can affect the behavior of the flow field, which will affect the particle behavior. However, in our case, mainly the flow, we have upward flow, and the rising plume of the occupants are the main cause that will affect the flow behavior. So neglecting the presence of furniture surely will affect, but will not have a significant effect on the particle behavior. For this reason, as this model is simplified, we didn't take into consideration the presence of tables or other furniture. Any other questions?
I have questions. Yeah? You talked about the certification height.
Yeah.
I mean, usually in design, okay, where do we place this certification height? Where do we like to have this certification height?
Usually, we just say that we should have the certification height above the bracing level.
Why?
Because as I said, below the certification level, the air is upward, while above it, it's downward, which makes it a critical zone where particles accumulate. When we are dealing with tracer gas completely follows the airflow field. So the tracer gas will accumulate at the stratification level. So if we ensure that the stratification level is above the bracing level for tracer gas, it will be okay. But the critical inhalable range doesn't cover only tracer gas, but also active particles which have gravitational effect. And the gravitational effect might lead to accumulation of particles below the stratification height. For this reason, it's not enough to have the stratification height a little above the bracing level, but we should have at least 30 centimeters above the bracing level to ensure that the particle with high diameter will not be able to reach the occupied zone.
Okay, final question. You talked about modeling, okay, and there are a lot of models, but how would I trust the results of the model?
Okay.
Did you do any validation?
Sure. any models that is developed should be validated. We used literature studies, doing CFD simulation to validate our model. And recently we used experimentation to validate also this model, which was extended to use chair frames to enhance the performance of the DV system. Because as we can see, we used a much high flow rate to ensure a good indoor air quality for the whole inhalable range, which is not energy efficient. So we should go and find new engineering strategies to be implemented to displacement ventilation in order to maintain a good indoor air quality while reducing the energy consumption.
Yes.
Well, I have just a comment. Really great presentation. Congratulations. And for your infection modeling, as we know that for the bacterial particles are in the range less than 2 micron. Yeah. Will you just make a comment, what happens to the particles that are in the range of 2 microns? Because you mentioned you have studied from 0 to 15 microns. So can you just make a comment about that?
Up or down?
Down. Okay. For example, here we can see the behavior of 1 micron particle. I tried to see how tracer gas behave, and I found that the behavior of tracer gas is very similar to the behavior of 1 micron particle. Displacement ventilation is critical for high particle diameters. For low particle diameters, the removal effectiveness of displacement ventilation is very good. And for tracer gas, I will obtain similar results than for 1 micron. You can see that the effectiveness of the DV is highest for 1 micron particles because the gravitational effect is lower, and nearly we always have the peak at the stratification level because the particles are carried by the airflow field easily as gravitation do not oppose the upward motion. So I can say that tracer gas will behave very similarly to 1 micron, and the displacement ventilation is very effective for tracer gases.
Thank you very much.
Thank you. This will bring it to the end of this session. Thank you.
Presented by Mr. Didier Coulon. He's not only a very dedicated and qualified technical person, but he's also very close to us. He works with us very closely in the region. And Monsieur Didier is an engineer, graduated from École Polytechnique in Paris. Also has another degree, École Nationale des Génie Rural d'Eau and des Eaux and de Froid, Rural Engineering, Water and Forest. He worked earlier for the French Ministry of Agriculture, and he also worked for the French Ministry of Research. He was the deputy director for the technology division that they have. He served earlier as Secretary General of the CIRAD, which is French Organization of Research for Developing Countries. He is presently he's been elected as a director for the IIR, International Institute of Refrigeration, since 2004. Mr. Didier will speak about very important topics, and he's been working on a very challenging issue, which is phasing out HCFC without increasing greenhouse gas emissions. He calls it the challenges. So we'll at the end. Okay, I leave the floor for Monsieur Didier.
Thank you, Walid. Thank you, Walid. Well, first, I would like to present you the International Institute of Refrigeration in a few slides. And then I would like to present you the needs we have in refrigeration. I mean, of course, you are perhaps not involved in all the refrigeration uses, but it is very important to understand all the refrigeration uses and the increase we have in the needs of refrigeration, because we have all the same technologies. And so we have to take into account all the uses in order to see what kind of policies we will have in the future in your country, in all your countries. And then I will explain the refrigerant issue, which is the main issue of phasing out hydrochlorofluorocarbons without increasing greenhouse gases emissions. And finally, I will try to tell you what the kind of solutions we have. So the International Institute of Refrigeration. We are first an independent intergovernmental organization. I mean, we have governments as member countries, including Lebanon. We are scientifically based. I mean, we have some statutory bodies with a Science and Technology Council. Our aim is to promote refrigeration knowledge and associated technologies, and of course that improve quality of life in a cost-effective and environmentally sustainable manner, including food quality and safety from farm to consumer, comfort in homes and commercial buildings, of course, including air conditioning, health products and services, and you will see what kind of needs we have in these sectors, low temperature technology and liquefied gas technology, energy efficiency, and last but not least, use of non-ozone depleting and low global warming refrigerants in a safe manner. It is our slogan here, our official slogan, and of course, it is not, it is a word to present at the end, use of non-ozone depleting, low global warming refrigerants in a safe manner, and you will see, we will understand afterwards why. We have member countries worldwide in all continents, developed and developing countries. We have experts in all these countries, and we also have corporate and private members, which are universities, private companies, consultants. We have publications, FreeDoc, which is a refrigeration portal. Our aim is to collect and select various articles in various languages from all over the world, and we build that in a database with now more than 100,000 references. We publish journals, the first scientific journal, the International Journal of Refrigeration, which has the best scientific journal in this field if you compare the various impact factors of the journals. We publish a newsletter, a quarterly your newsletter. We publish books, guides in various fields, informatory notes for decision makers, statements also in United Nations conferences on the ozone layer, on climate change, on the food safety, because of our status, intergovernmental status. We organize conferences, IR conferences, sometimes corporate conferences with other organizations. In all these fields, in all these refrigeration technologies and uses. We have some working parties. We participate in some research projects, not as a research organization. We are not making research ourselves, but we are involved in some research projects, international research projects, where we are in charge of the bibliography and also the dissemination of the results. And also we are involved in some preparation of standards. Once again, we are not proposing ourselves standards, and we are not a body which is publishing standards, but we are preparing, we are involved in various technical committees in the ISO and various intergovernmental organizations. The first important message I would like to give you is the fact that we have increasing needs of refrigeration, and because of these increasing needs of refrigeration, and when I mean refrigeration, it includes air conditioning, we have increasing energy and environmental challenges. Refrigeration is everywhere. For instance, in cryogenics, with traditional industries such as petrochemical refining or steel industry, for instance, as well as more modern industries like the space industry, nuclear fusion, all the various industries. Of course, you don't see that there is refrigeration. It is a hidden technology, but you have refrigeration in almost all the technologies, including the information technologies, nanotechnologies, biotechnologies, and so on. Refrigeration is more and more used in the health sector, medicine and health products, in cryosurgery, which is currently developed, anesthesia, in scanners, in vaccines. You have more and more health products which needs to be kept and transported in a certain range of temperature, and thus you need refrigeration if you would like to keep them useful. In air conditioning, of course, in buildings, data centers, cars, various vehicles. In the food industry, in the cold chain, for instance, to manufacture the food, to prepare the food, but also to transport it, to store it, to commercialize it. Of course, also domestic refrigeration in your apartments or houses. In the energy sector, including heat pumps, we consider that heat pumps is one of the refrigeration uses. It is exactly the same kind of system you have as refrigeration. It is reversible heat pumps or heat pumps for air conditioning or for heating. In liquefied natural gas, for instance, you have more and more gases which are used in energy, especially currently liquefied natural gas, but perhaps in the future hydrogen. And of course, to liquefy the gases, you need refrigeration. And liquefied natural gas, for instance, is currently very fast developing compared to other kinds of transporting the gases. Environment, for instance, of course, you know that we try to develop carbon capture and storage, and for that you need refrigeration for selecting the CO2, and afterwards to storage it. You have public works. You have to isolate the soil for some public works. Leisure activities, of course, also in mountains and so on. Well, I will give you a few data illustrating the fact that we have increasing needs, especially in developing and emerging countries. First, of course, the USA are not a developing country, but it is, of course, if there are some problems in the US, you will have also problems in developing countries. We calculated a few years ago that there were about 1,600 deaths in the US per year due to pathogens and at least partly associated with temperature control, and of course, probably many more in developing countries. Another data, according to the World Health Organization, an intergovernmental organization from inside the United Nations, refrigeration and improved hygiene have reduced stomach cancer by 89% in men and 92% in women. I don't know why the difference, but well, since 1930 in the US. And another estimation from this United Nations agency is that you have about 3 million deaths per year which are related to refrigeration worldwide. As you probably know, we have a growth in global population, particularly in Africa and South Asia. The current prediction is that we will have about 9 to 10 billion people in 2050, and among them, you will have 8 billion in developing countries. And last but not least, you will have 70%, about 70% in 2050, 70% of people will be in urban areas. Currently, you have 50%. The increase will be very low in developing countries. It is essentially in developing countries where they will have a the number will double in developing countries, in urban areas. And thus, because you will have more people in urban areas, will increase the need for cold chains due to longer distances between production sites and markets. And you will have also more progressively more westernized models with, for instance, the meat, which needs, of course, more refrigeration than cereals.
Yeah, sorry.
Please.
The
3 million deaths are related to refrigeration or lack of refrigeration?
Lack of refrigeration, I mean. Of course, well, that is, I'm sorry, it's too short. Of course, lack of refrigeration or not enough refrigeration.
I thought they froze to death.
Not at all, or sometimes because you don't have enough refrigeration.
Okay,
a lack of refrigeration. Currently it is better than these figures. I'm sorry, it is not now 1 billion, but 80,000 people who are 80,000 million people who are undernourished. So it is decreasing, even if the number of people is increasing within the world, you have still a lot of undernourished.
Oh, yes.
Okay. Okay. We calculated that we have in developing countries about 23% of food losses, which are caused by a lack of refrigeration, versus 9% in developed countries. These figures are not including the consumers. I mean, of course, in developed countries, you have more problems within the consumer. The consumer are not keeping, are probably, the behavior of the consumer in developed countries is not so good than in developing countries. I mean, the 23% and 9%, it is for the transport and storage of food. The post-harvest losses, except the consumer losses. Also, you have to understand that needs related to better health are global. We need a reliable cold chain, air conditioning, specifically to an aging population. The older you are, the more refrigeration you need and more air conditioning. And for instance, you have also a recent study from the Massachusetts Institute of Technology, which showed that mortality during hot days, temperatures higher than 32 degrees Celsius, decreased by 80% between the period 1900 and 1959 and the period 1960 to 2004 in the US. And according to that study, the adoption of residential air conditioning explains essentially the entire decline in the temperature-mortality relationship. And it is very important to understand that, of course, it is not only, air conditioning is not only a kind of comfort, it is also useful for health, and especially for aging populations. And of course, you know that all over the world, and especially in developed countries, you will have more and more people who are old, will be old. So increasing needs, especially in emerging and developing countries, means increase in environmental impact. We have two consequences of these increasing needs. First, energy consumption in refrigeration equipment, including air conditioning equipment, must be reduced because, according to our latest estimation this year, we have about 16% of worldwide electricity consumption, which is used for refrigeration, including air conditioning. And of course, it is much more in Middle East countries due to air conditioning use. So it is not negligible, of course. You also the fact that you need to reduce the energy consumption in refrigeration equipment is due to the fact that you have lack of energy resources in the future and indirect global warming impact, which is the most. You have a lack of infrastructures. You have some problems, including in the US, but also in India, for instance. You have a problem of infrastructures, the problems of cost of electricity in the future. And you must know that the indirect global warming impact, because of the use of fossil fuels for the electricity production, is the most important one. It is much more important than the environmental impact, global warming impact of refrigerants, due to refrigerants. However, people focus for various reasons on the problem of refrigerants. Because most refrigeration equipment uses refrigerants, And despite of development of alternative technologies, and I will tell you a few words about that, vapor compression systems using refrigerants will prevail over short and medium term. So, a short history to understand the current situation regarding the refrigerants, because I will now focus on refrigerants. First, at the beginning, when the refrigeration becomes a worldwide technology, we have had a lot of various refrigerants. But beginning of the 20th century, progressively, chlorofluorocarbons became the reference refrigerants, except in the food industry where ammonia was still used a lot. Unfortunately, in 1974, we discovered that there was a hole in the ozone layer, the stratospheric ozone layer, and thus, after a lot of various negotiations, there was an agreement. The Montreal Protocol was signed in 1987, and the aim was to progressively ban all the products containing chlorine as well as bromide. And of course, refrigerants were, at that period, contained chlorine with chlorofluorocarbons, as the name, you see the name. And afterwards, there were discussions and negotiations about global warming. After the Rio Convention in 1992, you have the Kyoto Protocol for certain countries in order to reduce the greenhouse gases emissions. And you had several kinds of gases which were considered as greenhouse gases. And within these gases, you had the HFCs, hydrofluorocarbons. So, regarding the Montreal Protocol contains CFCs, chlorofluorocarbons, HCFCs, hydrochlorofluorocarbons. You still have chlorine in HCFCs, not in HFCs, hydrofluorocarbons, but HFCs are, have a global warming potential as well as CFCs and HCFCs, and I will show you afterwards the kinds of importance they have. And thus, because of the Montreal Protocol, you have the phase out of CFCs with some dates which were for developed countries, other commitments for developing countries, and now you are in a period where you have to phase out HCFCs, hydrochlorofluorocarbons. It's already started in developed countries. It will start, and it starts now for developing countries, including Lebanon. Well, in this table, I hope you see the figures. You have the left column, the various families of refrigerants. The second one, the main refrigerants in these families. Then a column from ozone depleting potential, and the column of global warming potential of the various refrigerants. As you see, you have CFCs, the chlorofluorocarbons, are bad refrigerants, both for ODP, ozone depleting potential, and for global warming potential. When you go to HCFCs, it's much better. You have a very low ozone depleting potential, and you have a global warming potential which is moderate. When you go to HFCs, the next step, hydrofluorocarbons, you have zero ODP, but you have a global warming potential which sometimes is very low, sometimes it's very high. For instance, HFC 404A has a global warming potential which is higher than the current HCFCs. And you must understand that going from HCFCs to HFCs without any distinction between the various kinds of HFCs is certainly not good for the climate. At the bottom of these HFCs, you have what we call HFOs, which are unsaturated HFCs. Currently, the figures for the HFC 1234YF is not 4, but according to the latest studies, it is a little less than 1. So it is very good. But you have a range which is very high, between 1 and about 4,000. You also have natural refrigerants, what we call natural refrigerants. You have hydrocarbons, You have ammonia, carbon dioxide, air, water, which have a very low global warming potential. And of course, zero ozone depleting potential. So you have some figures which are from the UNEP report, and we participated in the review of this report. So you have the CFCs, you have the consumption in kilotons, you have CFCs, then HCFCs, which are increasing because, of course, they replace CFCs, and HFCs, which are replacing both CFCs and HCFCs. And so you see in 2010 the level of the various kinds of refrigerants. And if you have some scenarios which are weighted by CO2 equivalent emissions, okay? These graphics are with CO2 equivalent emissions. So you have CFCs, which are, as I explained you, are bad. But afterwards, you have an increase of HFCs. Of course, it's normal. They are replacing CFCs and HCFCs, and in addition, you need more and more refrigerant equipment, and thus more and more refrigerants. So you have various scenarios, and of course, in the worst scenario, in the future, probably in 2050 or a little afterwards, the impact of HFCs, if you don't do anything, would be relatively similar than the impact of CFCs at the beginning regarding the global warming potential. So it is not a catastrophe, but it's important. Currently, HFCs are representing about only 1% of the greenhouse gases emissions, CO2 weighted, okay? About 1%, so it's not a lot. And if you include all the various kinds of refrigerants, it is about 2%. So it is relatively negligible, but because of this increase, it will be important. And you cannot consider that it will be negligible in the various international negotiations. You have various scenarios. According to us, the most probable will be about 7% in 2050 if we don't have any additional measures against this increase of HFCs consumptions. So, and 7% is not important. It's more than, for instance, the airplanes and so on. So in any case, you have to do something. Here, it is you have the various uses of HFCs. As you see now, HFCs are mainly for refrigeration and stationary air conditioning. It is in yellow. In blue, you have mobile air conditioning. Mobile air conditioning is very important. You have foam agents in gray, and it is relatively negligible, aerosols, fire retardants, and solvents. Okay? So in any case, if you would like to reduce the HFC consumption and emissions, you have to reduce the emissions in refrigeration, stationary air conditioning, and mobile air conditioning, as well as foams. And, well, now I would like to explain you the international context. So, since 2009, each year, you have North America, I mean Mexico, US, and Canada, and Micronesia, with also some other islands, Mauritius and so on, which propose an amendment to the Montreal Protocol in order to phase down HFCs. To phase down, it means that the idea is not to phase out HFCs, because we consider that some HFCs are relatively good for the climate. I mean, for instance, HFOs and so on are certainly the impact is much lower than the current HFCs. So the idea is to phase down the HFCs up to 15% of the baseline. And since 2009, you have emerging countries, especially India and also Gulf countries, which refuse such an amendment. And thus it is impossible to have an agreement because you don't have an agreement of all the countries. And the Montreal Protocol was signed by all the countries. They refuse because, first, they consider that HFCs are not included in the Montreal Protocol. They are included in the Rio Convention and the negotiations on climate change because they are not, they have no impact on the ozone layer. because they consider the need to continue to develop refrigeration, including air conditioning. Of course, they need to continue to develop its use. And they consider that there are some problems of cost, efficiency, availability of other technologies than the current HFCs in hot climates. So, well, it's a little boring, but since 2009 and until this year, you have the same kinds of negotiations without any result between people who would like to have a phase down of HFCs and countries which wouldn't like to have it. But you have to understand that in any case, the issue, the conclusion will be a phase down of HFCs, whatever the success of the negotiations, in my opinion. First, you have to know that, well, of course, the European Union is not a model. I'm European myself, but it is not a model. However, it will, the policy of the European Union will have an influence all over the world. It already has some influence in the policy of the US and policy of Japan, and it will have an influence on all over the world. What is the European Union policy? First, in 2007, it decided to build what we call the F-gas regulation, flirted gas regulation. The aim of this regulation was to reduce the leakage because of a better maintenance and thanks to a certification of companies, certification of people, training people, and thus the idea was to reduce the emissions without any commitment regarding the production and consumption of HFCs. So F-gas regulation, and also in 2007, a MAC directive. It means Mobile Air Conditioning Directive, because as you saw, the mobile air conditioning emissions are very important. You have a lot of leakages. So in that case, people decided to totally phase out the current high GWP HFCs. And in the MAC directive, according to this directive, since this year, all the new series of cars have to use low GWP HFCs or natural refrigerants. Currently, the two technical solutions are either HFOs, HFO 1234YF, and most of the car manufacturers are chose this refrigerant. You have some German car manufacturers, Daimler-Benz, and in the future, Volkswagen, who preferred to use CO2 as the refrigerant. But, and it is a progressive phase out, because now there are the new series of cars. In the future, all the new cars will be built for these refrigerants. And because the impact of this regulation, of course, will only allow the European Union to not to increase the emissions, but not to reduce enough the emissions of HFCs, and the European Union would like to reduce by 80% in 2050 their emissions of greenhouse gases. They decided to phase down HFCs. In addition to that, to phase down HFCs, building quotas, it means that starting in 2015, all the companies which are selling refrigerants will have quotas of refrigerants, and progressively they have first 100%, then 90%, and 80%, and so on, until 2030, where the base will be 21% of the current baseline. Okay, so it is a progressive phase down with some bans also. The highest global warming potential refrigerants, especially, for instance, depends on the various applications, but for instance, the R404A will be banned in the near future in the European Union. And also in some European countries, you will have some additional bans or taxes. So in addition to these European Union regulations, you have some European countries which are also taxing the HFCs according to their CO2 equivalent potential. In addition to the European Union actions, we will have an increasing international pressure, not only from the European Union or North America or other developed countries, but also from companies. I mean, companies are developing There are new refrigerants, they are developing new compressors, new equipment, and these companies would like to have a worldwide market. So you will have an international pressure, including from the private companies, which are located in Europe, in Japan, in the US, and so on. We have the development of alternative technologies by these companies because of these regulations, which are progressively taking place in Europe, but also now in the US. They are preparing some new measures in Japan, and so on. The main date you have to keep in mind is 2015, because in 2015 you will have in Paris a United Nations Conference on Climate Change, and the aim is to have commitments of all the countries in order to phase down greenhouse gases. And if there will be a success, there will certainly be some measures regarding HFCs. I don't know, of course, which kind of measures, perhaps including HFCs within the Montreal Protocol or not. But in any case, you will have some decisions regarding HFCs if it is a success or a partial success. In my opinion, because of these international negotiations, because of this, the strategy of the private companies, worldwide companies, you will have a phase down of high global warming refrigerants in the near future, with or without an international decision. And HFCs must not be replaced by high GWP HFCs, and alternative solutions are needed. So, what are the various technical solutions? First, you can have refrigeration technologies without any refrigerant, so you will have no problem regarding that, of course. And you have some various technologies: magnetic refrigeration, electrocaloric cooling, cryogenics. It means that, for instance, you have liquefied nitrogen, you diffuse it in a certain area. You have absorption, including solar refrigeration. We are working a lot in these various technologies, for instance, solar refrigeration, not only because of the energy issue, but also for the refrigerant issue, magnetic refrigeration and so on. Within the IR, we have some working parties, conferences on these topics, also research projects we are involved in. So there are numerous technical developments in all these technologies. However, we still have some problems of cost, first investment cost especially, of efficiency of these technologies, the capacity of these technologies. So in the near future, there will be only niche technologies. But in the long term, it could be different. Secondly, and it is certainly short-term solution, you can reduce the leakage. For instance, it was the policy of the European Union to reduce the leakage. Because you have important variability within similar equipment, working under similar conditions, there are certainly margins for progress regarding leakage. The F-gas regulation in the European Union will strengthen controls on leakage. Reducing leakage would avoid an increase of the global warming impact of refrigerants in Europe, but not a reduction. Training is the biggest obstacle. And we certainly have to increase training all over the world regarding leakage. However, reducing leakage has clear advantages, not only in terms of the environmental impact, but also in terms of savings. Of course, you will save some refrigerants, but also on safety. And it is very important to understand that safety, I'll speak afterwards on that, is a key issue. And of course, if you reduce leakage, you will reduce the risks, the safety risks, which is important not only for high global warming refrigerants, but also for low global warming refrigerants. Secondly, reducing the refrigerant charge. This concerns also both the safety and the reduction of greenhouse gas emissions. And thus, research and development focus on all refrigerants, for instance, including natural refrigerants, secondary refrigerants, and microchannels. So you have, as well as the reduction of leakage, reducing the refrigerant charge is a good way to reduce the impact and to adopt new refrigerants. We publish inflammatory notes. I can't tell you more about our publications on that, but I would like to insist on these technologies, which you don't need in any case, in all the cases, to change the refrigerants. But it will not be enough. I would like to insist also the possibility of using secondary loops, not only because secondary loops is a good solution for reducing the refrigerant charge, to reduce the leakage, because you concentrate the risk. And for safety, it's very important to consider the risk in a certain place, which is much more controlled and without an impact on the public. For instance, for supermarkets, it is dangerous to have hydrocarbons in supermarkets. You have had recently an accident in New Zealand, which was a very big accident. If you concentrate the refrigerant in a certain location, it is much better. You have, for instance, the development of district cooling in various countries, in Europe, in China. I know that in Qatar, we are working with Qatar and district cooling, with Lebanon, yeah. Dubai, yeah. There are various solutions. You can, of course, have to design a new system, but you have to think about new systems. And of course, if you are engineers, it is a good opportunity to design new systems. And finally, last but not least, in any case, you will have to progressively choose lower GWP refrigerants in a perspective of phase down and not a phase out of HFCs. So the solutions I will present you regarding the choose of lower GWP refrigerants are linked with a phase down, not a phase out, but currently a part of some environmental, non-governmental organizations. Nobody tries to totally phase out HFCs. Of course, you will need a sector-by-sector approach depending on outdoor conditions, especially regarding hot climates. Well, what are the various possibilities? First, you can use lower GWP HFCs. And currently, you have the development of R32 in Eastern Asia, and some companies, important worldwide companies, are trying to develop R32 with various equipment using R32 in Asia, but now probably worldwide within a few years. And it will certainly be a solution because it is simple, it is very well known, the cost is low. However, it is mildly flammable. The problem is that it is only moderate GWP, about 720. So you cannot use R32 in all the sectors. It is possible in order to phase down HFCs to use it in particular sectors, but if you use it, of course, in all the sectors, it will be a problem. But don't worry, they don't try to propose it in all the sectors. HFOs, which are unsaturated HFCs, have a very low GWP, so there is no problem regarding the environment. However, they are very costly currently, much more costly than the current HFCs. However, they have similar uses as HFCs. They are mildly flammable, as well as R32. But in any case, they are developing all over the world. I mentioned air conditioning in cars, but also companies which are producing HFOs are also trying to develop many more applications. These companies are also developing a lot of blends with HFOs, HFCs, hydrocarbons, HCFCs, for a lot of applications with moderate GWP or low GWP. Some of the blends are non-flammable, others are mildly flammable. Generally speaking, the lower the GWP, when you have very low GWP, you have some risk of flammability, but they are mildly flammable only. And you have natural refrigerants. You have CO2 as a refrigerant, which is currently mainly used in moderate climates in Europe, in Japan, for instance. But the companies are developing transcritical CO2 cascades, so trying to progressively go in warmer climates. ammonia, which is still used in all over the world, especially in the industry, but you have also some technical developments to use it in other kinds of applications. Hydrocarbons, you have an important development of the use of hydrocarbons in a lot of developing countries because, of course, it is very cheap. However, it is flammable, highly flammable, and thus there are some safety risks, and people have to care on that. Water, but it is, there are, for other reasons, it is not very developed. And of course, you have publications on that. Well, the conclusions are the following ones. First, with or without international decisions in 2015, there will be a phase down of high GWP HFCs in most countries, and it is starting now. So replacing HCFCs by these refrigerants in your countries is not a long-term solution. Secondly, air conditioning represents one of the most important uses of refrigerating equipment, both in terms of fluorinated gases use and in terms of electricity consumption. Moreover, it is rapidly increasing. So we cannot avoid changes in this sector. So you are involved in buildings, you have to take it into account. There is no simple solution, no easy drop-in solution such as the replacement of CFCs by HCFCs, HCFCs by HFCs. So you need to invest and to have some innovations as designers. Safety issues are important. Regulations might be adapted, and they are progressively adapting. I mean, for instance, the US recently decided to use hydrocarbons in domestic refrigeration. It was totally forbidden before, but because people understood that it is perfectly safe in the European Union, it is perfectly used without any big accident. So you have in France the government changed also its regulation regarding ammonia because it was almost impossible to use ammonia in France before. Now it is possible, according to it is only necessary to compare the various regulations all over the world, and you can adapt these regulations, taking into account the new technologies. A part of that, it is very important to participate in international standards definitions, and applying them is also necessary. We currently have a lot of discussions at the international level in ISO technical committees in order to progressively implement new standards or to adapt the current standards. So it is very important to be aware on these evolutions, on these negotiations, in order to prepare you. And unfortunately, developing countries, including warm climate countries, are not enough participating in the standard bodies. It is a pity because in these standard bodies, you essentially have people from North America, from Europe, from Eastern Asia. Not a lot from your countries. I fear that the consequence would be the fact that the standards are not perhaps first enough adapted to your countries, and you will not be able to rapidly implement them. In any case, it will be useful to reduce leakage, to develop adequate training for installers and users in order to reduce direct and indirect emissions and to avoid accidents. Since that issue is a key issue for the future of air conditioning, many technical developments are underway, mostly in developed countries with moderate climate conditions. However, technical solutions will be progressively adapted to warm and developing countries. A part of worldwide general works, conferences, publications, working parties, research projects, pre-standardization, there is involved in dedicated works for other countries we are working with you. And increasing needs of refrigeration, thus you have increasing energy and environmental challenges, and thus increasing needs of the IR. So you can become a member. Thank you. Merci.
I guess we could entertain some questions. We have about 6-7 minutes if anybody has questions for Mr. Didier.
Yes. Regarding the refrigeration, I think in the previous years, the refrigerant was really abused in manufacturing, and it's only just been utilized ineffectively and a way to, especially in manufacturing. Now, as we know, containment of the refrigerant within the system should be looked at more closely so that most of the time this refrigerant will be contained. So many alternatives in the future, but I mean, why not if you look at the containment of the refrigeration system and it's really controlled?
I totally agree, and it is the reason that I first indicated you as a solution to reduce the leakage, to have a better containment of the refrigerants. I totally agree. The problem is that with a better containment, we can avoid an increase of the use of these refrigerants and emissions of these refrigerants. But according to all the calculations which are already made, if you do only contain better these refrigerants, you will not reduce. The problem is that you also have in all the countries, and you will see what will happen in the next negotiations regarding climate change. You have to reduce all the greenhouse gases emissions. So not only to avoid an increase, but to reduce them. I think so. Even if you try to compare the best practices regarding containment, of course it is necessary, it is useful, but it will not be enough. And thus, in any case, you will have to also find other technical solutions. Of course, I agree, it is certainly also for the existing equipment, you will have to reduce the leakage because you will not change all the equipment in the short term. So for new equipment, you can design new solutions. For the older equipment, it is not better to simply reduce the leakage, and it's possible.
Thank you. Thank you, Didier, for a really excellent presentation, specifically the suggestions regarding the region. I have a question. I mean, the point you made about the standards organization and the involvement of the people from these countries in the standard organization. Can you give us a suggestion, or can you tell us if IIR can help in introducing these countries to those organizations, for instance? Because I'm sure we have a lot of expertise in the area, but we need to bring it up.
Well, we tried to explain to the various countries, and for instance, we participated in a UNEP event at UNESCO in July, trying to explain to the various representatives of the countries that they have to be involved in these technical committees. Of course, we need to have people who have time to do it, because it is time consuming. You need people who are aware on techniques, technologies. It is not something, it is sometimes complicated. But you also need some decisions of the governments. I mean, for instance, to participate in the ISO, you need to be a member country. It is like IAEA. The government has to ask to be a member country. Of course, if it asks to be a member country, it will be. There is no problem. But it will have a kind of involvement. You have various, in the ISO system, you have various kinds of member countries. You have member countries which are totally involved, countries which are only kinds of observers, or countries which are absolutely not involved. And unfortunately, when you see the countries which are totally involved, most of them are developed countries. I'm sorry, but that it is a governmental issue. Of course, we tried to convince the governments, and I tried to convince you that it's important, but I cannot decide without that. Go ahead.
So I have a question. It's a bit away from the global warming and the ozone. Actually, about the mobile refrigeration. By that you mean refrigerants in cars. Does that have any impact on the hazards, like on the drivers? If for example, any leak happened inside the car without us noticing, does it have any long-term or short-term health hazards?
Well, you are right. I mean, of course, one of the main issue we had when we tried to, because the only experience we have regarding mobile air conditioning using low GWP refrigerants is in the European Union with the MAC directive. Okay, according to that experience, the main problem was the flammability of the refrigerants. even if they are mildly flammable, there is a small risk if you have some leakage. And it is the reason that you have, even if most European manufacturers decided to use HFOs, which are mildly flammable, German manufacturers, currently Daimler-Benz first, but very probably in the near future Volkswagen, preferred to use CO2. CO2, the problem of CO2 is that you have a higher pressure, and thus you have to differently design the system than with HFOs. HFOs, it is relatively simple for a car manufacturer. You don't need to change the design of the car. It is different for CO2, and thus it is more costly for them. But effectively, it is a problem that they encounter.
Yeah, but it's not considered as a carcinogen or something that might cause cancer or something like that. Those that are currently being used.
The current refrigerant which is used in mobile air conditioning is R134A. Okay, it is the main refrigerant in these systems. It is not the worst one. I mean, the global warming potential of this refrigerant is about 1,300. So it is acceptable compared to, for instance, R4A and so on. But the aim is the problem of mobile air conditioning is the fact that you have a lot of leakage, and thus it represents a very important part of the emissions of HFCs, as I showed you in one slide. Okay, and thus the decision of the European Union was to completely phase out R134A. Okay. And very probably because, well, even if you have a lot of cars which are built in other countries than the European Union, it will probably be followed by other car manufacturers, even in other countries, in Asia, in America. So, in my opinion, in the future, not perhaps within a few years, but in the long-term solution will be either, it will be the same as the European Union, all the car manufacturers will adopt either HFO 1234YF, most of them, and some of them CO2.
Okay, one more question and then we have to close the
Should we understand that there is a big, considerable, major financial impact when replacing the current equipment using the HCFC to the equipment using HFC?
Well, of course it is a financial issue. It is financially, we don't need a lot of investment if you simply replace HCFCs by the current HFCs. It is not costly, okay? But if you would like to use lower GWP HFCs or natural refrigerants, you will have to pay attention first to safety issues, and thus even if you have some mildly flammable refrigerants, you will have some problems. Well, perhaps they are not adapted or they are adapted, but in any case you will have some problems of regulations, of standardization in order to adapt these new refrigerants and in any case to modify parts of the systems. So it is much better to do it for new equipment than for old equipment, because if it is new equipment you can design it differently.
Thank you, Mr. Dede. I'm sure this has really been a good keynote. As the title is a challenge really to phase out HCFC is not an easy solution. More on the subject will be given by another keynote tomorrow morning, also on this issue, and probably it will be presenting some more solutions to the problem. I want to thank the speaker for an excellent presentation. The audience, thanks so much. This afternoon we'll have 3 different sessions, 2 in this hall, another one on industrial application is going to be in the College Hall, Auditorium B, so if you're interested. Bashir will present. Bashir is here. But presentation is not over. It's there. Okay, good. So we'll go ahead and start with the first presenter, Ms. Elisar Yahya. She is Lebanese, living in France, currently a second-year PhD student in LGCGE, Laboratoire de Génie Civil et Environment, the Université de Troyes, France, holding a master's degree in French of research in civil engineering from University of Lille. She has diploma in civil engineering in 2009 from the Lebanese University Faculty of Engineering. She had worked before as structural engineer for 3 years in Beirut, and she's now going for her PhD. So, Elisar, your presentation is loaded? Okay. She will be speaking to us on efficacy of using a phase change material, PCM, as a thermal energy storage for building applications in the Mediterranean region.
Thank you. Okay. So I will be presenting the efficacy of using phase change materials as thermal energy storage for building applications in the Mediterranean region. Actually, we have started in France in our laboratory working on the phase change materials since several years. The application of these materials in France, especially in North France, is a little bit different from other countries because we have a very cold weather. So up to now, the efficacy is not that promising because till now we have realized that the phase change materials are actually acting as insulators more than energy storing in the cold weather. But we have we are going to enhance the performance of these materials during our project. And on the other hand, the applications on the Mediterranean region and in the hotter and the warmer regions have been a lot more promising. So I will be presenting a little bit the applications in these regions otherwise. Okay, so first the content of the presentation will be, I will introduce an introduction and a little bit information about the energy consumption in buildings, the classification of phase change materials and their role in building applications, the experience in phase change materials in different countries, especially focusing on the experiences in the Mediterranean regions, Greece, Cyprus, and other countries. We'll discuss the life cycle assessment of these materials, and last but not least, I will present our proposed or developed numerical model that I was working on during my PhD, which is based on a mesh-free method, which is the lattice-Boltzmann method. It's a very new numerical model, and some conclusion. Okay, so what is a phase change material? A phase change material is a substance with a high heat of fusion. When melting and solidifying, it is capable of storing and releasing large amounts of energy. Heat is absorbed and or released when the material changes from solid to liquid or vice versa. So according to the statistical review of the world energy in 2013, oil remains the world's leading fuel with a consumption of 33.1 global energy consumption, while the hydroelectricals and other renewables have less percentages, and especially in the undeveloped countries, the rely on the fuel is very important. So any enhancement or any decrease in these consumption will make a difference. It's not the similar case as in other developed countries. Why the concern in PCM? In the past decade, the economic situation started to change due to the rise in energy prices. Hence, researchers start to give more attention to the application of phase change materials for heating and cooling in buildings. As you can see, the number of researches that are concerned in the latent heat storages and phase change materials have been increasing from 1994 till now 2014. So the energy consumption in buildings, according to IEA 2008, we have 30% in USA, while in Europe it increases to 40%. Still less than the world average, which is 50%. But in the undeveloped countries, like Lebanon, we have a 70% consumption of energy just in buildings. So as we said before, any enhancement on this, on the decrease of this energy consumption will be attractive. So how do we classify the phase change materials? First, the phase change materials can be classified as organic, inorganic, and eutectic. The major used in buildings are paraffins and salt hydrates. The choice of the phase change material for building application is according to the melting or fusion temperature, which should be within the thermal comfort temperature of a human being, which is about 23 to 26 degrees Celsius. The role of phase change materials in building: during the day, they absorb heat while melting and consequently reduce the indoor temperature. While at night, when the room temperature are low, the phase change material rejects the stored heat, thus preventing the temperature in the room from getting too cold. So we have some regulating temperature function. As we can see here, when we don't use the phase change material, we have a very high temperature fluctuation according to the thermal comfort of the room, while when using the phase change materials, this fluctuation will decrease very much. Another example is that phase change materials will improve the thermal mass. As we can see here from the diagram, we have the phase change material of 1 centimeter thickness have a thermal mass which is comparable to, for example, 20 centimeters of sandstone or 23 centimeters of concrete. And according to the gypsum, also is much more high. So we can see how the thermal capacity and thermal mass of these phase change materials is high. So how can we apply these phase change materials in buildings? In buildings, they can be applied in suspended ceilings, as we can see from the figure. In the day, the hot or the warmer air will pass through above the ceiling and get a little bit colder, and then rejected to the room. And vice versa, at night, the colder air will go through the ceiling and be a little bit warmer. So that we can apply it in ceilings. We can apply it in plaster boards, concrete, with micro-encapsulated paraffins or paraffin powders. They can be applied in the blinds, and the floor, and also in the latent heat storage systems. What are some experience of phase change materials in buildings? In 1997, Anthony and their partners made some experiments on PCM gypsum board in a passive solar building. The total temperature in the room was decreased by 4 degrees Celsius. In 2014, Zalowski and partners, which is our laboratory, we have made some experiments on the mortar with micro-encapsulated phase change materials. We have noticed 41 increase in the stored energy or the energy which is released. A little bit about the experimental devices that we are using in our laboratory. We test some samples of different dimensions. This experimental device consists of 2 exchanger plates connected to the thermostat baths to ensure the required thermal conditions. The samples are placed between these 2 plates. Heat flows are measured using heat flux sensors. The data acquisition station is connected to a computer from which we control the thermostatic baths. As we can see, this is a picture of the machine. Another experiences were done in the Mediterranean region. In Cyprus, also in 2012, made some experiments. There was noticed a decrease of 1.6 degrees Celsius in a temperature of 14 millimeter, 1.6 degrees Celsius in temperature for a 15 millimeters phase change material, with a reduction of 41.2 in cooling energy. This was applied in for a house with a low thermal mass. Little efficacy was noted for higher thermal masses buildings. In Cyprus, also, Peniotto and their partners in 2013 used a macro-encapsulated phase change material. There was noticed also a 28.59% of energy, while this amount increased when we used an adequate insulation with the phase change material, which proves that when using a phase change material with an adequate insulation, we have better performance of the phase change materials. It increased to 66.17 in reduction. In Greece, in Mandilaris and their partners made an experiment on an unoccupied typical house with no energy system. They used multi-layers of insulation materials with gypsum plasterboard panels containing phase change materials. There was a decrease in the decrement factor from 30 to 40% and increase in the time lag of 100 minutes, which means that we have increased the thermal mass of the buildings. In Spain, experiments were done on cubicles with salt hydrate phase change materials added to the walls. Energy consumption decreased by 0.86, which is not very good. But when they used set points closer to the melting point, this increased to 15%. So this we come to a conclusion that phase change materials showed a better behavior during the summer conditions than during the winter, as we said, because they behaved a little bit like insulation, and they showed better performance when they are used with the adequate insulation, and when they are used for a longer period of time. As for the life cycle assessment, the process, as a definition, the process used to quantify and evaluate the environmental impacts known as life cycle assessment. So why are we discussing this? This is the aim is to analyze if these energy savings are large enough to balance the environmental impacts originated from the manufacturing of phase change materials, and also because phase change materials originally, one of the disadvantages of using them is their initial high costs. So also we are going to discuss the return period of these phase change materials and if it was promising. So as we can note that phase change materials must operate as long as possible during the year to reduce the operational impact. Second, the phase change materials benefits increase in locations where the weather is a little bit, the conditions are similar, so that we can use it more cycles and during the year. Salt hydrates as phase change materials were found to be better than paraffins in reducing the manufacturer costs. The payback of global of phase change materials was less for salt hydrates than for paraffins, and it was like there was a study in Cyprus for a building. When they didn't consider an insulation, the payback period was 14 years, but when they used an adequate simulation insulation, it was 7.5 years. Still, this is according to because we have initial high costs of phase change materials. Now, according to the numerical model, we have developed a numerical model based on the Lattice-Boltzmann method, which is a mesh-free method. Lattice-Boltzmann method has a tendency to simulate complex physical problems, including multi-fluid flows, heat transfer, solute transport, phase changes, or the presence of multiple phases, complex geometries, and porous medium. It was a little bit challenging to start with this numerical model, but this model has a little bit more tendency to be developed, and because of the simplicity in numerical modeling and its wide tendencies. So Lattice-Boltzmann method has been achieving great success in these fields since its emergence because of its distinctive advantages over the conventional CFD models. A brief view on Lattice-Boltzmann method. Who is Ludwig Boltzmann? Actually, Ludwig Boltzmann is an Austrian physician and mathematician who is regarded as the father of second law of thermodynamics and statistical mechanics. Ludwig Boltzmann has committed suicide after in his early 60s or late 50s because he was very prone to high criticism due to the emergence of his kinetic theory of gases, his major achievements actually afterwards. After years of his death, everyone has been convinced by the presence of the kinetic theory of gases, and 80 years after his death, the numerical model was implemented for a Lattice-Boltzmann method. So what is the Boltzmann transport equation? This equation describes the statistical distribution of one particle in a fluid. The distribution is defined such that F, which is the density function, is the number of molecules which are at a time t have positions lying within a d cube r and having a momentum which is around d cube p. So the main two steps of the lattice Boltzmann method are the collision step and the streaming step. We have this is a mesh-free method. We have lattices. Each lattice has a certain number of velocity vectors around it. As we can see here, this is the 2D D2Q9, which has 9 velocity vectors. In the streaming step, the vectors will propagate according to their direction of velocities. And in the collision step, the particles will collide, exchange energy according to Maxwell-Boltzmann distribution, and then we will have the new distribution function. The macroscopic velocities, densities, temperature, and all the macroscopic values are determined from the summation of these density functions around each lattice node. As we can see, this is the lattice Boltzmann equation. It contains the time variation, spatial variation, effect of a force acting on a particle, and the collision term. This collision term is a complex integral differential term, but it was then simplified to a single relaxation time lattice Boltzmann method that is only related to viscosity. So it became a very simple equation. So here note that Fi can represent a velocity field, it can represent energy field, it can represent temperature, any order parameter. So only one simple first order differential equation to represent the whole physics. By the same equation we can calculate the temperature, we can calculate the velocity, but we have to use many, like 2 distribution functions to calculate the velocity and the temperature. So for each field we have to use a distribution function. So for phase change materials, the phenomena of melting and solidification are widely presented in many industrial applications like geosciences, industries, and materials. So our aim is to develop a numerical model to simulate the phase change process and apply it to phase change materials. Lattice Boltzmann model is used to couple thermal convection. We have introduced the convection and melting, and it can be easily modified to account for thermal transfer due to convection and diffusion. The mathematical formulation includes the continuity equation, the momentum equation, and the energy equation. As for lattice Boltzmann model, we use 2 distribution functions, velocity field, one for the velocity field and another for the temperature field. As we can see, these 2 simple equations, discretized equations, when choosing the tau f, which can be is the relaxation factor, which is related to the viscosity, we can retrieve the momentum equation. And when using the tau h, the heat transfer relaxation parameter related to the diffusivity, we can retrieve the energy equation. Here we have added also a Boussinesq force. This force is added to the velocity, the fluid velocity. And we have also added in the energy equation the source term to account for the phase change, and it is added in the collision distribution function. The numerical model is verified through a well-known benchmark problem. As we can see, we have a phase change, whether in a rectangular or square cavity. Results, as we can see, with respect to the liquid diffraction, results match the results created by Haber, Christian Haber, and Jurabian. And the melting fronts and the position of the melting fronts are they match the expected melting fronts by Jenny and Bidjan in 1987. As we can see, the position of the melting fronts for different dimensionless time, we have transformed from a conduction to a partial convection to a fully convective regime. Optimization of phase change enclosure. We have in my PhD we were working on an octadecane in a plexiglass for the glass facades. So we have started our experiments on an octadecane plexiglass, on a plexiglass containing octadecane with an aspect ratio of 20, which is 1 centimeter versus 20 centimeters. Due to when we have applied the numerical model, we have tried to optimize the enclosure, the dimensions of the enclosure, to have the better performance and better energy storage, and then to order another samples with the new dimensions. So the optimal shape was with the aspect ratio of A equal to 4 H/L instead of A equal to 20. As conclusion, our experimental results show that phase change materials are more effective in hot weather than act as insulators in winter. The application of phase change materials on the envelope of dwellings in Mediterranean countries is considered to be a very attractive solution in terms of energy savings and comfort. Nevertheless, a major disadvantage is still in the high initial cost of phase change materials. The previous experiences show that the integration of phase change materials in buildings with an adequate insulation would improve the thermal capacity and reduce the energy consumption. The increasing number of studies in phase change materials in many Mediterranean countries like Cyprus, Greece, and other neighboring countries, therefore should set it into discussion in our country, in Lebanon, where energy saving is vital due to the increasing price of fuel, which is our major rely. It would be interesting if a test sample is conducted on houses in our country, or at least a numerical simulation model for an implemented one. Thank you.
Thank you. We could entertain a couple of questions. Anybody has a question for Elisar?
Thank you for the nice presentation.
You're welcome.
One question.
Yes.
What's the lifetime of the phase change material when you install it in the house? And you came up with a 7-year payback period, 7.5-year payback period?
Yes. Actually, it's considered that the lifetime of the material should be equal to the lifetime of the building, which is the maintenance, which is around 50 years. So when we talk about 7.5 years of payback, when we are in a country that is relying mainly on fuel consumption, it will be a little bit more promising. But when we are talking about, like in France, it's more. We have we can see that the life cycle, because the phase change material acts as an insulation. We have a little bit more colder weather, so it will be a lot of more return period. So it won't be so promising.
You mean a shorter return period or longer? Longer, so
yes.
Rather than 7 years, like 10
maybe
years.
We didn't test the case on a room or on a small house.
But still, you're going to be getting the rest as pure saving.
Yes.
Did the test that maybe make a problem in condensation?
Sorry?
Maybe they will have a problem in condensation.
Yeah. For the phase change material?
Yes.
We didn't encounter this because we are just moving from a solid to a liquid, and from a liquid to a solid.
I'm just wondering, you're talking about a typical example that you're using the plexiglass.
Yes.
What are these changes in plexiglass in the normal operating conditions?
As phase changes, when we put we are using plexiglass as an enclosure only. We are putting in the plexiglass an octadecane. An octadecane has a melting temperature of 26 degrees Celsius. So it can be changed from solid to liquid when the temperature drops from 26 or goes up to 26. The plexiglass is only for the enclosure.
We'll take one more question.
Your case studies are mostly concentrated on the moderate part. What do you expect to happen with those change materials in extremely hot climates?
Yeah, actually the phase change materials in the hot climates have in the literature shown better performance, and I think they have used phase change materials, macro-encapsulated phase change materials in some stations in Qatar. So I think it would be very much more promising.
Thank you, Elisar, for this nice presentation. Please start with around if you have any more questions with the partner after the session. The second speaker for today is Ms. Rina Annan. She's a mechanical engineer. She received her Bachelor of Engineering from the AUB in 2010 and her master's degree in Applied Energy in 2013 from the AUB also. She's a lead accredited professional with 4 years experience in the energy modeling and the condensation and acoustic. She works at Dar al-Handatha as a mechanical engineer. So she'll speak about the optimization of the building envelope in hot and climate conditions.
By Ben Sumner, the head of energy modeling team at Beirut and myself. Today I will be speaking about the optimization of building envelope in hot and humid climate. So, we will go over the objective and methodology, the building envelope optimization. I will go over some cases, parameters under study, then we will go over the simulation results. Furthermore, we will study the moisture control, hydrothermal assessment, and acoustic analysis and noise attenuation. So what's the objective? The objective of this study is to promote building sustainable design to reduce energy consumption by implementing optimized building envelope for high-performance buildings. Also, to study the moisture influence of the thermal performance of the construction and the long-term behavior, and to validate the noise mitigation due to outdoor equipment, and propose solution for noise in the indoor occupancy. The simulation tools needed here are IES, WUFI, and CADNA. We will study 4 different cases to the building function. We studied offices, residential buildings, airport, and convention centers. So the weather files were mainly located in hot and humid climates, including Dubai, Makkah, Riyadh, and Al-Madinah. So the weather data. Hot and humid climate must be given extra special care since problems related to excess moisture can occur more than drier climates. The relative humidity exceeds 80% and reaches 100%. All our cases are located in hot and humid climates. The annual simulation weather files are taken from Meteor Norm software version 6.1. Among the weather data that we studied, we took the Dubai weather data. And here we can see the yearly variation of the external dry bulb temperature and the relative humidity. We noticed that the dry bulb temperature reaches up to 40 degrees Celsius, and the relative humidity reaches to 100%, which might cause problems. So this table shows the parameters under study. As you can see, all of the cases, we focus on the parameters window-to-wall ratio, the U value of the external wall, and the glazing, and finally, the shading coefficient of the assembly. All of these cases are compared to a baseline case, which is obtained from ASHRAE. So what are the parameters on the analysis? We will start by the external opaque construction. The thermal insulation is added to the opaque assemblies of all building types considered from cases 1 through 4. All the propositions of the building envelope components, as we said earlier, are compared to a base building wall and roof assembly in ASHRAE. The baseline wall, external wall is characterized by an insulation installed within the cavity of the steel stud framing and has a thermal resistivity of 1.42. Also for the base wall, it has a continuous insulation over structure that with overall thermal resistance of 2.78. Moving on, the second parameter under study is window-to-wall ratio. It is important to limit the window-to-wall ratio in order to minimize the heat exchange coming from the outdoor hot and humid climate into the internal cool conditions. Based on ASHRAE also, the perspective building envelope option recommends that vertical fenestration to be less than 40%. In all our cases, the window-to-wall ratio is below 40%. So this table here shows the external wall insulation and the roof insulation, the type and the thickness. The shading. And the 4 cases we studied, we have Islamic arcade as shading, also extruded overhangs and multiple vertical fins that has been used. Further on, the shading coefficient. It is known that the lower shading coefficient, the lower heat gain into the building. The three levels of shading coefficient that has been used is 0.28, 0.4, and 0.2. Finally, as been seen in the table, the results compared to the baseline, we got 35% saving, annual children energy load percent saving in case 1, 5% in case 2, 3%, in case 3, 20%, and 10% in case 4. So what's happening in case 2 and 4? You notice that they're lower than the other 4 cases. Basically, this is the lower saving is due to the presence of unshaded skylight. So we have a high glazing to roof ratio of 9% to 4% in cases 2 and 4. Also, in case 2, having a very low saving, this is due to the fact that the shading coefficient is 0.4. This is basically higher than the ASHRAE baseline. Okay, so we're done with the building envelope and with the optimization that we did. Further to this, we want to obtain more comfort, more occupant comfort. So we address the hydrothermal assessment. So what are the parameters needed for this assessment? 3 main parameters are needed, which is basically the external environment conditions, the interior environment, and the thermal vapor properties of the wall structure. So the first recommendation, it is important to seal the building assembly to reduce the air leakage coming from air cavities in the wall and the ceiling. Also, the temperature at each wall construction layer, referred to as the interface layer, must be greater than the total dew point temperature of the whole assembly. And finally, in order to prevent the potential of mold growth and condensation, the relative humidity at any layer of the construction must be less than 75%. So let's take a case study. A condensation analysis has been performed on case 2, which is the bilateral 5, which we earlier saw the external dry conditions and relative humidity. So the hydrothermal simulation has been done in MUNIB for 3 consecutive years. The figures below show the variation, the annual variation of the temperature and relative humidity. The temperature is in red, and the relative humidity is in green. This represents the insulation layer of an external wall, and this represents the roof, the insulation layer at the roof. We notice that the relative humidity is decreasing, and the temperature reaches around 40 degrees Celsius. However, the relative humidity is decreasing around 65%. And the roof, the relative humidity is around also 68%, and the temperature is around 22 degrees Celsius. Further to the optimization, supplementary advantages could be by reducing noise. So we also took another case study. And we studied for case 1 other buildings with cooling towers located at the roof. The manufacturer's data gives a solar power level of 110 dBA, and this is considered as noisy and not comfortable. The indoor sound level with occupied other rooms is recommended not to exceed 30 dBA. So what's next? How can we deal with this issue? The proposed solution would be by having a wall with 80 mm mineral fiber insulation with noise reduction of 65 dB, coupled with a double glazed assembly with RWCTR of 37 dB, used with glazed sections of the elevations and allows for adequate sound transmission to the occupied spaces. So we have a reduction by using this type of insulation and this type of double glaze. What about the outdoor noise? Okay, so as we can see, the cooling, a maximum of 80 dBA at the cooling tower top at the roof, of which the cooling towers are placed. So we see that it's 80 dBA around it. Also, we're interested to check the outer facades adjacent to it, and we notice that it's 84 dB. This is also large and can be noisy. So what's the solution? So, optimized solution mitigation measures. It is by adding vertical sound barrier system, providing sound reduction of 12 dB, and silencers with potential reduction of 25 dB. So the final results, as you can see, will indicate 61 dBA at maximum. Okay, finally, what's the conclusion? The main objective of this study was to investigate the building's sustainable designs that can bring significant performance benefits in order to reduce energy consumption. The parameters under study were window-to-wall ratio, the U values of the wall, and the U values of the glazing and their corresponding shading coefficient. The annual chiller energy load % saving achieved for the 4 case studies compared to the baseline ASHRAE 90.1 model with respect to the proposed design models are achieved due to the optimization of the above-mentioned parameters. And finally, sustainable high-performance design is further coupled with prevention of the transmission of hot and humid air and high disturbing noise into the occupied spaces, thus enhancing indoor air quality and occupant comfort. Thank you.
Thank you. Thank you for the presentation. We could entertain a few questions. Anybody has questions?
Yes. Now regarding the building materials. Now, as you know, we have so many building materials that can be also utilized to enhance. What kind of building materials do you consider for the, especially in humid areas and the exterior? I mean, the barriers and so forth.
Yeah, this is basically, we start by studying if it has condensation, especially in hot and humid climate. We study the layering of the construction, and first of all, we check if it has condensation or it might cause mold growth, especially in such climates. And then we would look at by trying to do some saving and comparing it by the baseline set by ASHRAE. So we have several options. We try several options in order to come up with the best solution that would actually save energy by using IES. IES is a software that helps, and by building the model inside it, with having different types of walls and simulating it. And the simulation will show me different values, and accordingly I will decide which is the best solution.
Thank you. Any more questions? Of course, energy efficiency could always be met by decreasing the U values. The question is, are the industry ready for that? Of course, the solar coefficient also is a big issue, but I think the industrial prospect of glazing, for example, and mold will have certain limitations. That's why we cannot go all the way down to more stringent values, because there's no industry that they could adhere to these kind of values. So, thanks enough for this presentation. Thank you. Okay, the third speaker, Mr. Bashir. Bashir, before we start, thank you for everything that you're doing in this conference. Has been great help. He's been working behind the scene. He's a person you could really depend on. Thank you. Engineering master students at the American University of Beirut. His is going to be present a talk on the use of energy regenerated membrane desiccant system to control the humidity and decrease energy consumption in office buildings. Okay.
I'm presenting this paper on the behalf of my colleague Khader Kenyal. I worked with him on this paper in my final year project, and he's abroad studying for his PhD, so I'm gonna take over to present his work. First, we're going to talk about a brief introduction about all the conventional HVAC systems, going through the objectives of our system, describing our system, and then talking about the theoretical model of the system. The main objective behind our system is to use a solar regenerated membrane desiccant that is used to control the humidity and decrease the energy consumption inside a closed room. In the future, we can reach to a passive dehumidification system that can work on its own due to sustainable energy. The proposed system is a hybrid system of air conditioning system that uses the novel liquid desiccant along with permeable membrane, and this will be integrated with the conventional HVAC systems to independently control the humidity and the temperature. The conventional liquid desiccant systems dehumidify the air usually before it enters to the indoor space. And this proposed cycle will dehumidify the indoor air directly from the space using the permeable cylindrical membranes that will act as a dehumidifier in one stage and will act as a regenerator as we will see in another stage. The air leaving the indoor space, will be also cooled using evaporative cooling to ensure that the liquid desiccant that's entering the space will not impose a sensible load on the closed space and will not increase its temperature, and also to increase the potential of the liquid desiccant to absorb more moisture from the indoor space. The size of our system is quite significantly reduced compared to the old conventional cycles that usually uses cooling towers and regenerator or even desiccant wheels. It's important to control the humidity and the temperature for three main reasons. The first reason is because of the sustainability of the building material or the energy consumptions, and for most importantly for the thermal comfort of the occupants inside the space. To eliminate this negative effect of moisture level inside indoors room, we can use either conventional or non-conventional techniques such as desiccant technique. The conventional techniques usually cool the air before it enters the inside the room to the due temperature, where it will condenses and it will lose all the excess moisture, followed by a reheat to have another increase of temperature for the air to make it adequate for the indoor space. Two main issues can rise from using such a technology of the desiccant technology. Mainly, the direct contact of the desiccant, and this might cause some health issues because some desiccants might be toxic. And for example, lithium bromide, which is toxic. So that's why in our experiment, we replaced the lithium bromide by calcium chloride. The second one is that dehumidifying the air outside the indoors room will require us to have the air that's coming inside the room to be at a much lower humidity ratio than the indoors air room. And this will require a very strong desiccant, and this desiccant might be strong on the behalf of being toxic. But fortunately, some studies and the HAMP studies have shown that direct cooling and dehumidification is effective. Actually, it responds directly to the change on the latent and the sensible load, and it does not require for a strong liquid desiccant to be needed in the experiment. The HAMP, which is the heat and the moisture transfer panels, is able to control both humidity and the relative humidity and the temperature using the liquid desiccant as a working fluid. This panel absorbs the moisture directly from the room, and the main concern about this HAMP was the ability to regenerate the desiccant or even cool it, the energy needed, the energy consumed to regenerate this or to cool it. In our study, the dehumidification or the regeneration ability of the membrane material will be modeled. And also we will compare its efficiency of the membrane to those of the conventional systems. This is a schematic diagram of a conventional system that is used. And this shows the path of the first oval ellipse shows the path of the liquid desiccant. The other one, and these are all the components, and these are for evaporative cooling. These are other complicated and not compact conventional techniques that are used. This is the HAMP technique that I just talked about, and this is for our system. I will start from number 7 along all the way to the closed loop. The liquid desiccant will enter the indoor space at a temperature low enough to allow it to absorb all the humidity inside the air room, and it will exit at 2. Exiting at 2, and the pipes where the liquid desiccant will enter are made of permeable membrane that will allow the transfer of water vapor, but not liquid water. And the pumping here is in solid pipes that will actually be heated by 2 sources. The first source is a heat exchanger that will be heated by the flow that's coming back from the regeneration pipes, And it will be cooled, it will be heated also by the solar heat input. The solar heat input is made of mainly parabolic heat collectors that are supposed to collect and store heat inside a storage tank. And this heat will allow the liquid desiccant to reach a temperature. We call this temperature a regeneration temperature, where it will be able to, if it passes through a permeable membrane, to lose all the absorbed water vapor to the ambient air. After it goes out from the regeneration pipes, it will be cooled by two heat exchangers, the auxiliary heat exchanger and the heat exchanger that is actually heating the liquid desiccant. And to ensure that the temperature will not impose any sensible load increase inside the indoors room, and to increase the potential of the liquid desiccant to absorb more water vapor, we will cool it by evaporative cooling before it enters the room. After describing our system, we will have to derive a mathematical model. Mainly, we will derive the mathematical model for the dehumidifier and for the regenerator. We will validate our mathematical model by experimentation, as we're going to see. And then we will integrate the proposed dehumidification system with the conventional air conditioning systems. In this picture, we can see a cross-sectional view of the permeable membranes. This cross-sectional view is modeling the resistances of the heat transfer and the mass transfer through the permeable pipes. The permeable pipes that were used, actually, it was propor, 3M propor, or polypropylene. Each term is for the outside or the internal convective, and similarly for the mass transfer resistance. The liquid desiccant and the permeable membrane are modeled by energy balances and species balances. The energy balances model the solution and models the solution that's coming in and out of the system. And we can see here that we have difference in partial pressures. The difference in partial pressure actually will be the force that will cause this transfer of water vapor from inside the indoor space to the permeable membrane at low temperatures, and at high temperatures it will reverse. It will flow from inside the liquid desiccant pipes, permeable membranes, to the outside room. And this is finally the model of the room, indoor space. We have an energy balance, and we have a species balance also, because it's losing. Actually, these results are for our low scale. We experimented this system on a very small scale system, and we managed to put 4 sensors, 2 at the inlets of the dehumidifier and the regenerator, and 2 sensors at the outlets of the dehumidifier and the regenerator. We can see that the temperature of the 4 readings coincided on one line, which is a good aspect, because this shows that the temperature remained constant while we have variation in relative humidity. The temperature in this case was, we can see that here it's 0.24 volts, which is 24 degrees. And we can see that the dehumidification was successful, because from 78, at a peak of 78%, we achieved a 60% relative humidity. And this was on a very small scale experiment for our final year project. This validated our model, and that's it. And thank you so much for your attention.
Nice project. Anybody has a question?
Josh, you mentioned that the system in the future, it will function on its own to be sustainable. But in the model that you showed us, there was a pump. How would you work about that?
We can model our system sometimes as a thermocyclonic loop that will depend on the buoyancy forces of the liquid desiccant to initiate a velocity gradient in order to have a circulation. And then we will not need the use of a pump in this case. Half of the loop will be inside the indoor space, and half of the loop will be in the outside space. And this will not make us lose the pump, because we will have this velocity gradient that will circulate in the liquid.
So it will be circulating on its own. You don't need a pump.
No.
Is this technology
also valid for the bigger volume space, big rooms, or just?
Yes, it is, but the size, this had a factor because the size of this was compact. Because we rather not use the big cooling towers or desiccant wheels, so we actually wanted to make it for a compact size, but for sure it works for a larger scale, for sure.
Any more questions for Bashir?
I just want to make an announcement before you close. Okay. For all our speakers who are residing in Crown Plaza Hotel, there will be transportation to the dinner location starting at 8. Dinner is at 8:30, but they will pick you up and take you to Phoenicia, and then we will take you back.
Thank you for the note. I'd like to conclude this session by thanking the speakers. We have 3 excellent speakers. It's good to see new blood evolving from all this effort, and I'm sure there is a lot of good stuff will come out of it. Thanks so much for the speak. Thanks for the audience for being gentle, and looking forward to another day tomorrow full of technical stuff. Thank you. Thanks so much.